A promising alternative is to the migration logic above the OS layer into the language virtual machine. Language virtual machines such as Java and WebAssembly abstract away ISA differences. Several previous studies achieved live migration for Java, OCaml, and WebAssembly interpreters, but those methods rely on interpreter-based virtual machines, so they are limited, so they are very slow execution. So let's compare hypervisor-based and interpreter-based approaches. A hypervisor-based system such as CRU and then captures a low native process state such as CPU register and memories. Because of its simplicity, its advantage is performance, and it incurs no runtime overhead until live migration happens. But program and their snapshot are ISA specific, so you can only restore on the same architecture as the host node. And interpreter-based interpreter-based system instead serialize the VM state into internal state, such as bytecode program counter and stack frames and heap object. And that state is portable across ISAs. But the problem is performance, because interpreted execution is very slow. So in this work, we improve interpreter-based solution by using ahead of time compilation, shortly LT. And our method bridges the gap between high performance and cross ISA portability. So our goal is to design a cross ISA live migration technique that achieves both portability, which means program is migratable between different architectures, and also our method achieves high performance. And our approach is to develop a WebAssembly AOT compiler that adds machine code level instrumentation to support efficient checkpoint and restoration of programs. And in the figure below, the compiler compiles WebAssembly into the native executable. And this executable can migrate between, for example, x64 and ARM64. So let me briefly explain about WebAssembly. WebAssembly, shortly WASM, is a portable binary format designed for safe and efficient execution. And WebAssembly uses stack-based virtual instruction set similar to Java bytecode. And each variable in WebAssembly module is statically typed, so it is suitable for AOT compilation. And WASM can be generated from languages, general programming languages such as C, C++, Rust, and Go. Although originally WebAssembly is designed for browsers, it's now widely used outside the web. And next, a WASM module contains functions, global linear memories, and tables, which are used for indirect function calls. And these abstractions make WASM execution portable. On right-hand side, we can see an example of WebAssembly function. This function returns a double of a parameter of type i32. And the first bytecode, local.get, pushes a parameter on a value stack, and the second bytecode pushes constant i32 on a value stack, and then the third bytecode, i32 multiply, pops those two values from a value stack and pushes a product of them. So WebAssembly natively does not support live migration functionality, so we need to implement some functionality to achieve live migration for WebAssembly program. And to migrate a WebAssembly program, its runtime state has to be portable. And similar to previous researches, our approach reuses the program state of a WebAssembly interpreter as a snapshot format. And the snapshot represents abstract WebAssembly state, which contains a program counter and call stack, locals, and linear memories. During migration, the source runtime checkpoints this WebAssembly state and transfers this snapshot into the destination runtime. And then the destination node then reconstruct the state and resume the execution. For example, a WebAssembly program precompiled x64 can migrate to another host where the same program has been compiled to ARM64. Only the snapshot data moves between them here. So to enable live migration for LT compilers, we need to instrument code to checkpoint and restore the execution. So here we considered two options. First one is WASM level instrumentation, and it transforms WebAssembly bytecode and insert the bytecode to checkpoint and restore. So this approach needs no runtime support, but resulting binary is large and very slow. And the second approach is machine code level instrumentation. It inserts machine code or compiler intermediate representation during lowering WebAssembly into machine code. And this approach is small binaries compared to the first solution, and it incurs only low runtime overhead. But it requires runtime support to capture and reconstruct program state. For these reasons, we choose the second option because we focus on performance. And LT compiler normally strip away all WebAssembly type information during lowering WebAssembly into machine code and compiler optimization. And this makes it hard for the runtime to reconstruct a WebAssembly level snapshot from row-level CPU registers and memory. So our key challenge is therefore how to rebuild WebAssembly state from optimized machine code without losing type information. So we leverage a technique called on-stack replacement, shortly OSR. And in JIT compiler, OSR switches between bytecode and optimized code. And OSR is also used for tiered JIT compilers. And in such cases, OSR switches between different level of optimized code. And OSR is implemented with a data structure called stack maps. And this data structure records where each program variable is located in register or memory. So we extend this concept of OSR to live migration of ALT compilers. So during a checkpoint, OSR translates the native code stack into a virtual WebAssembly stack. During restore, it reconstructs the native frame again. This allows us to capture and reinstantiate the execution state safely at certain program point. So for example, to make a checkpoint, the runtime performs OSR exit to convert its native program state into virtual WebAssembly state. And then the runtime can save this virtual WebAssembly state as a snapshot. On the other hand, to restore the execution, the runtime performs OSR entry. This is the opposite operation of OSR exit to convert the virtual WebAssembly state into native program state, so that it can reconstruct the state from virtual WebAssembly state to some CPU registers or native memory. So here in this slide, we introduce a new concept, migration point. And migration point represent program point where the program can be checkpointed and restored. At each migration point, a tiny code snippet shown below in this slide is inserted. This code snippet checks whether a migration request has been issued. And if the migration request is triggered, then the runtime starts checkpoint operation. For example, it unwinds the code stack. So, however, pressing a migration point after every bytecode instruction would cause heavy overhead. Instead, we insert migration point only at function entries and loop bodies. Here we insert migration point at the loop inside the loop bodies so that we make sure that the runtime can migrate even when it executes in the infinite loop. So these program points correspond garbage collection safe point, where the garbage collector typically starts the garbage collection. And this design reduces the runtime overhead while making sure that the program can be migrated. However, migration point act as a compiler optimization barrier. So certain compiler optimization, such as code motion and dead code elimination across the migration point are disabled. Otherwise, the runtime could no longer reconstruct the correct WebAssembly semantics, and it diverges from the original semantics of a WebAssembly program. So, and in implementation, we implemented these ideas in a prototype compiler called Wanko. And Wanko is based on the WASCA compiler, which compiles WebAssembly to object files with LLVM compiler infrastructure. And we extend WASCA compiler to insert instrumentation mainly during the lowering from WebAssembly into LLVM IR. And Wanko also has a runtime library, and it provides state capture and reconstruct functionalities. And these functions, calls to these functions are inserted by the AOT compiler. And the output of our compiler is a machine code binary, and that can be migrated across different ISAs. So in evaluation, our experiment addresses these 4 questions. First, how much runtime overhead does instrumentation add? Second, how much does it increase code size? Third, how fast are checkpoint and restoration? And fourth, how large are the snapshot? So first, runtime overhead. We compare Wanko with 2 AOT baselines, WebAssembly micro runtime AOT and WASM-H AOT. And you can see the black dotted line in this figure, and this represents the baseline of our compiler. And this compiler does not do any instrumentation. So the output of this compiler can't be migrated across different nodes. And without this machine code level instrumentation, Wanko performs similar to both of WebAssembly micro runtime, which is shown in orange, and WASM-H AOT, which is shown in red bars. And with instrumentation enabled, the average slowdown is 36%. This is shown in blue bars. And I think this overhead is acceptable given that we gain the ability to migrate across ISAs. Next, checkpoint and restoration times compared with CRU. CRU is a tool to migrate Linux process to another Linux, and it is limited to migrate the same. It is limited to migration between the same architecture. And across all benchmarks, Wanko achieves shorter checkpoint times than CRU. Restoration time varies more widely depending on program structure and heap layout, but still it remains competitive. Although our machine code level instrumentation enables fast migration operations. And next, snapshot size. Snapshot size is another advantage. We compare the snapshot size of Wanko with that of CRU. As I mentioned before, CRU is to migrate Linux process, and Wanko max 1 to 26 times smaller snapshot size than CRU. And the next step in the next evaluation, we measure the code size, and the instrumentation does increase code size. At the machine code level, it roughly doubles the binary size, about 2 to 2.5 times larger. For comparison, we also implemented WASM level instrumentation using 18CFI. 18CFI is one of the passes implemented in WASM optimizer, which transform WebAssembly bytecode, and output is also WebAssembly bytecode. And it turns out that this WASM level instrumentation produces more than 4 times increase. It's worse than machine code level instrumentation. So our approach achieves a good balance between functionality of live migration and compactness of code size. So in conclusion, we developed a WebAssembly compiler that supports live migration by instrumenting machine code. And our proposed method achieves both portability and good performance. And this imposes 36% of runtime overhead in average. And last, future work includes external state capturing, including file system and TCP and UDP socket, and further reduction of the runtime overhead. That's all. Thank you. Sorry, can you repeat the question again? Mm-hmm. So the question is, if I understand correctly, the question is that the snapshot of our approach is portable across different WebAssembly runtime. So the answer is yes, and we designed snapshot for this purpose. And basically, our snapshot contains WebAssembly call stack, and each call frame contains a program counter. And in the bottom, for the middle of call stack, it might be a return program counter. And the snapshot also contains global variables and linear memory, and it corresponds to a state of WebAssembly interpreter. So I think we can achieve also portability across different runtimes. But we need to implement state reconstruct and checkpoint mechanism for different runtimes.
Nice, thanks.
Thank you.
Okay,
Uh,
is it possible to reduce the frequency of the migration point to improve performance?
Hmm. So I think to reduce migration point means program can't respond shortly after it catches migration request. So
I think there is a trade-off between the delay of the migration
yes,
and the overhead.
yes. So I think we can reduce significantly migration point, but we need to investigate this trade-off between this delay and performance. Thank you. what do you mean by capabilities?
Where like file system permissions and permissions for other operating system level interaction.
So what is your question?
Do you assume the same set of capabilities at the source and destination of the
Mm-hmm.
migration?
Oh, so in the current implementation, we only focus on core specification of WebAssembly, and it doesn't contain functionality such as calling to system calls and opening files and socket. So we only focus on migrating core WebAssembly state. So it only contains basic value stack in WebAssembly virtual machines. So yeah, so I think supporting file system and you mentioned as a capability. So it is one of the future works.
Thank you.
Okay, it's good time to switch to our next talk. So thank you very much. Goes by 1 year, etc. Now we have switched to. Maybe we can. There is no way. Okay. I was expecting to have my two ends. Okay. Hi everyone. So first of all, I don't want you to be disappointed. I will not be presenting anything new regarding compilation techniques. The only thing I will be presenting is just a mere report of what we have observed as a result of compiling to WebAssembly. So first, I will start with a gentle introduction for those of you that are not extremely familiar with WebAssembly. So although some of these aspects have already been presented, I will still go with my slides. So WASM is a virtual machine that has been, I think, initially designed for running fast application on the web. It's an open standard, meaning that there are several implementations that are compatible one with each other. It's a low-level VM, and we will see that in details. It's type-safe, great. And it has no standard library, which is kind of unusual, especially if you compare to the JVM, which has this huge set of Java classes. So the core language of WebAssembly is low-level arithmetic operations. It's a stack-based structure. You push and pop values from the stack, but you have global variables and you have temporaries. You have functions, and we will see that. It has a standard binary format. It has a tool chain where you can compile, assemble, disassemble, profile, debug, these sort of things. And it has two external syntaxes. Let me dig into this particular aspect. What you see here is an implementation of a recursive Fibonacci function expressed in WebAssembly. So sorry, just one end, not easy. Here you see the regular Fibonacci function. You have a parameter x to a function called fib. In WebAssembly, all user identifiers are prefixed with a $sign. And here we make the comparison of this parameter x with 2. If it's smaller than 2, we return 1. Otherwise, we compute x minus 1, and we make the recursive call and the second call, and we sum up, and we are done. The same thing, exactly the same program, we can implement it with this S-expression-like format, which is absolutely equivalent, and it gives you the illusion that there is a structure in WebAssembly, although it's just exactly the same thing as before. And by illusion, what I mean is that actually I can have 3 parameters to the call of fib, and it's fine. I will just be pushing 3 values, and fib will be popping 2. But since I have added this add thing here, I will pop the extra value, and everything is fine. So you see the two formats are absolutely equivalent. Also, when you are using a Lisp-like system for implementing something related to WebAssembly, this format based on S expression is extremely convenient because you get the parser for free. And so we are very happy with that. Okay, so WebAssembly is pretty small, but on top of the WebAssembly machine, you have a full-fledged of extension over there. And the ones that are interesting for us, compiling dynamic languages, are probably exceptions that we need here. Where are exceptions? Exceptions are over there. And of course, garbage collection. It's a very useful extension that comes with a type hierarchy. And we have also things that we like very much in the scheme community, which is tail call and these sort of things. So let me present that. The garbage collection extension, it comes with a hierarchy of type that are now available on WASM programs. And this hierarchy is you have a general type, you have a subtype of it, which is a type of values that are comparable with the EQ predicate, and you have subtype for that. How do you use this thing? Here is an example of the implementation of Lisp lists, if you want. You define a pair type, which has just a car and a CUDA, which are two references of any values. And here is the implementation of the list copy function, where you take as parameter a list that might be empty, and the empty list here is represented by the null value. Then you are able to check if something is a null value with this predicate here. If it's null, you return another null value. Otherwise, you access your list, and I will try just with one end. Here it is. We extract the car of something, and the way you do that is you say, I'm considering the local parameter O. I will extract the property car of something which is a pair. And on top of that, I will put that in a new pair that I allocate with this struct new thing. And this is provided by the garbage collection extension, which is great because now it's very close to what we need for compiling Lisp or ML or whatever. So this is not the only thing we need slightly more, and in particular we need another extension, which is function references, which basically give you pointer to function. So next to the previous hierarchy, we have the func type and func ref type, which is just pointer to function. So pointer to function is not closure. So if you want to implement a closure, you will have to use some encoding similar to what you would be doing with assembly or C code, which is you will have to build your own data structure for closure, which is what we do here. Oops, sorry. Here we define the type of closure, which is just a pointer to a function and an environment. And here we implement the scheme function for each, which accept a function and a list, and we apply the function to all the elements of the list. And this is exactly what we do here, where we call the function. From this data structure, we extract the entry point, which is pointer to function. But since WASM is safe and is type safe, we have to cast this into a function which will take two arguments, the environment and the actual value. So this is a cast here. And now we can call this pointer to function, and we are applying the function to all the elements of the list. Great. With that, we are almost happy. The last bit we are missing is a connection with the outside world, because at some point we will need to implement our library. And what we have been using in our settings is external value using JavaScript value. And the way you do that is you have this new type, extern and extern ref. And in this example, I show you how you can manipulate a JavaScript bignum from within JavaScript. You will declare a type, which has an extern ref as a payload, and then you will refer to JavaScript functions that are accepting as argument an extern ref. And here I'm implementing in WASM a predicate that tells me if a big num is 0 by just invoking the JavaScript function which is there. Okay, so far so good. Sorry, I have been fast. Now, what we have been doing with WASM is checking what's going on with managed languages when they are compiled to WASM. And by managed language, basically what we mean is languages that use garbage collection and that are either functional or object-oriented languages or dynamic languages. The kind of languages we like. So we try to collect all the language we could, but we restrict ourselves to real language that are not experimental, language that are meant to implement real application, if you like. We also restrict ourselves to languages that are decently easy to install. We didn't want to go to all the hassle of installing all these crazy things. Robust implementation. We want to be able to run kind of actual benchmarks. And something important for us, we wanted multi-backend systems because we wanted to compare the performance of compiling to WebAssembly versus compiling to pre-existing backends, so native code or something like that. Okay, so these are the language we have been able to put our hand on and that we have been able to play with. So let me start with GHC, which is Haskell. So here is the performance of Haskell compilation when compared to native Haskell. The red line is a native Haskell compiler, and the blue bars are the ratio in between what you get with WASM and with native compilation. So the first observation that we have to make here is that the GHC implementation of WASM is extremely robust because all the benchmark runs, which is kind of great. But you have to pay a price, which is something like a 8-time ratio when you are comparing the performances. We didn't do any reverse engineering, but what we have understood here is that Haskell is not using the garbage collection extension, so it is using everything by itself. So it is implementing its own stack, its own GC, its own everything. So our guess is that if you are not using the extension, the 8x ratio is something that you have to be ready to pay for if this is the way you want to go. So the other implementation we try is Dart. Dart is easier to install because when you get Dart these days, you get all the backends of Dart without any extra operation that you have to do. So you get a native code, once again, the red horizontal line, and you get also a JavaScript backend and a WASM backend. And so what you observed here is that Dart is decently robust, mostly all the benchmark runs, and you get more or less same kind of performance as you can get if you are using the JavaScript backend. Although JavaScript for some reason seems to have a problem implementing big nums because e-digits and pi-digits are using big nums, so maybe there is something weird with the implementation in JavaScript with big nums that makes somehow the whole picture that I'm presenting here not totally fair for JavaScript, but still, you see with WASM you have more or less the same performance. If you are really interested in building web application and you want an extensive connection with JavaScript, not sure that it is so interesting to use WASM as of today, and maybe you can stick to JavaScript. It's kind of up to you. So the other language is Ruby. So as you can see, Ruby is not as robust as what we found with Dart because half of the benchmark are not really running with this in this language. And you see the kind of performance you can get. It's in between 2 and slightly more than 10x if you are using Ruby. And once again, it's just a Ruby that you can download and install on your machine and run the benchmark, and this is the kind of thing you will observe. Then the next beast is OCaml, and OCaml is interesting because it has several backends. And first thing, what I'm comparing to here is OCaml-C, which is not the optimizing compiler, it's a bytecode compiler. So I'm comparing JavaScript and WASM to the bytecode compiler for OCaml, and the reason why we are doing that is that JS of OCaml and WASM of OCaml are actually based on the bytecode compiler. So we thought it was a fair comparison. And what you see with the purple bar are the performance of OCaml native compiler. So you have all this performance in the same in this picture. And what you see is OCaml is extremely robust. It compiled very well. And actually, there is no missing thing. Sequence actually runs with WASM, but for some reason that we have not been able to understand, it runs infinitely fast. And it really runs. That is, it produces a good result, but extremely fast. And we have not been able to understand why. Maybe because the JIT is playing some tricks and there is some memoization or something like that. I don't know, but this is it. So you have good performance, not exactly as good as what you can get with a native compiler, but it's quite usable as is. Next system is Guile, which is a scheme implementation. And it's not the easiest one to install, as I must say. Maybe not so robust either, because 2/3 of the benchmark only runs. But Guile aims at being a complete scheme implementation with support for call CC and all this sort of bells and whistles we have in this language. So maybe this explains also why the performance of Guile is not so great in comparison to the native compilation, because you have to pay some price for manipulating the stack and so on and so forth. The last implementation is our implementation, another scheme implementation, but without support for call CC. So maybe it's a reason why we are able to be much more robust and much faster. And one of the interests of our implementation is that it's able to compile to native code, red line, to JVM bytecode, and to WASM bytecode. And to WASM code, sorry. So you see that it's quite comparable to what you get with JVM, which sounds like a remarkable result if you consider the expertise that has been put in the JVM and in WASM. And for us, we see this as a very promising result. So in comparison, just this table, and you see that for at least 3 languages, maybe there is something weird with OCaml. So let's say at least with Dart and BigLoo, we are in the range of 1.5x to 2.x compared to native code for WASM, which is kind of really great because you have some benefits in addition to the performance. So the other thing that we did is to try several possible compilation strategy, and we try to measure the impact of all these possible ways you have to generate WASM code. So the first thing which is kind of striking with WASM is that it is basic block unfriendly. And what I mean by that is you don't have go-tos in WASM. So if you represent your program as a call graph and just branch in between basic blocks, you will be doomed. You have to do something else. So typically, a normal compilation would look like something like that. You have a trampoline, and you have a local variable representing your program counter. You will just have a main loop, and from going to one basic block to the other, you will assign your program counter, you will loop, and you will just use a switch table to go to the next basic block. Hopefully, you can avoid this schema by using the technique presented in this great paper by Norman Ramsey that tells you how you can take your control flow graph and reconstruct the loop that you have probably had in the first place in your program. And we measure the cost of using this technique or not using this technique. And you see that basically, if you do not do this relooper technique, you will have a slowdown close to 2 on many benchmarks. So if you have one idea to keep in mind is that if you have to implement only one optimization when you are generating WASM code is implement relooper. The next thing we did is try to see what is the impact of using I32.1 ref. And these are just small fixed nums of 31 bits. So if you are willing to accept small integers only, what will be the benefit in comparison to allocated fixed num of 64 bits? And the performance is as follows. For most benchmark, there is no real penalty in allocating your fixed nums. And the reason for that is normally you use your fixed num for array indexes or these kind of things, and you can pre-allocate these small fixed nums. Only benchmarks that use big small fixed nums, such as Fibonacci, have to allocate them, and then you will start paying the price for that. The other thing we try is there is a great option in V8 is that you can run WebAssembly in an unsafe mode. If Andreas was in the room, he would have said this is no longer WASM. Okay, but for us, it's interesting to have a fair comparison with C, and C, you can compile unsafe code and things like that. So it's interesting for us to make this comparison. And you see that if you accept to have your program that crashes from time to time, well, you may have an acceleration of 30% or something like that. So this is maybe interesting for you. Then the last aspect I would like to present is type safety. This is a normal implementation of the scheme car function. What you do is you test that the value you received is really a pair, and if it's a pair, you access the car, otherwise you trigger an error. You may think that a normal implementation of WASM would be this one. You test if your value is a pair, which is the thing I'm doing here, and if it is a pair, you access it, otherwise you throw an error. No, it's not that easy in WebAssembly because WebAssembly is safe and it is not relying on occurrence typing or anything of this kind. So you have to test that something is a pair, you raise your own exception, otherwise you have to cast the value into a pair, and this may trigger an internal error. So actually you will be testing twice if the object is a pair. So what we have tested is what is the price we pay for this double testing, and here it is. That is, we generate code without any type test introduced explicitly by our compiler, and this is what you observe. So this is a kind of a limitation of WebAssembly. There is a technique for getting rid of this double test, which is using branch on cast here, that we have not implemented yet, so I cannot report on the benefit of using this instruction, but normally you should be able to get rid of this double checking. Okay, so I'm almost done. Some final thought for concluding this talk. First thing is, we see this platform as a platform very promising because we are able to get close to 1.5 regarding BigLoo as a penalty in terms of performance, and other systems are in the range of 1 to 2 when compared to native code, which is kind of remarkable. You have this idea of compiling once and running everywhere, and yes, indeed, it works. We are able to compile once our scheme program and to run them on the server and to run them on the browser, which is kind of wonderful. We are still missing some features, and in particular, we have no call CCs in BigLoo because we don't have basic operation for manipulating the stack. We don't have multi-threading, something that we miss. Implementing our runtime library is kind of a pain because we are missing things. We are relying on JavaScript, but the scheme library provide blocking I/O operation, and it's not easy to implement that when you just have non-blocking operation with JavaScript, so it's kind of a limitation. There are, for now, operations that we cannot implement. And there are some, I think, interesting problems. The problem is the not connection between traps, internal WASM error, and exception that force you to have some double checking. So I think that for type safety, we can avoid that. But for instance, for array bound checking, you cannot avoid that. You have to test that your index is in the array, otherwise you trigger an exception of your language. And then WASM will also test that the memory access is safe. So I think it will be difficult to get rid of all this double checking always. Then it's really low level. It's really just a bare machine without any library, without anything. So it means that you will have to implement your own linkers and loader, which can be kind of a little bit painful. And maybe one of the obstacles of compiling, it's not really generating code, but it's because you are lacking library, you will have to re-implement your library by hand. And regarding our implementation, it's about 50,000 lines of WASM code that we have written by hand. Thank you so much for your attention.
Interesting and really broad study. I wanted to ask about your comparison. So I think you're comparing sets of benchmarks, and actually different sets of benchmarks for each language against the native compiler for that language. What happens if you take, say, one benchmark and compile it to WASM with all your different tool chains? Which one does better? I mean, can you say something about the quality of WASM code generation for the different languages, or not really?
Not really, and we are not interested in comparing one language with the other. We just wanted to compare just the performance of what is supposed to be the best possible compilation for each language. So we wanted to compare GHC to GHC, OCaml to OCaml, and we wanted to avoid any war of...
is not interesting.
To me.
Were you able to measure the startup time and tiering time? So for compiling, the startup time for your benchmarks?
No, we didn't. We pay attention to have benchmarks that run at least 10 seconds each. So probably the startup timing is minimal and negligible. So yeah, we are using long execution time. And what I didn't mention is that we measure actually 2 WASM implementation, something you will find in the paper. So it's not only one implementation. Yeah.
Hi, so being from JetBrains, I must ask, why didn't you include Kotlin in your comparison? Is there any reason for that, or?
For not implementing, which language you said?
Kotlin.
Maybe we didn't think about it. We should have, I'm sorry.
It was interesting to me about the importance of using the GC and using the same stack. Those two things, though, are kind of separable. Do you have any thoughts on how you might test them separately, or will it just depend on having the right sort of implementation where you can pull those apart?
Could you be more specific in your question?
Right.
What do you have in mind?
Two of the things you talked about for Haskell, for example,
Yeah, yeah,
is
yeah.
that they're implementing their own GC and their own continuations, right? Their own use of the stack, right?
Yeah, somehow, yeah.
So you could imagine that maybe you're doing those two things differently, right? That in some other language implementation. Is there some way to peel apart the importance of reusing the GC versus reusing the continuations?
No, I don't know. The only way maybe to answer this question would have been to implement our own GC for our own scheme compiler. I think this would have been too much for this report. So no, the only evidence that I can provide is that apparently implementing your own GC with Haskell, performance-wise, is not so great. And for Bigloo, the GC extension apparently works very well, because 1.5, I was not expecting such a good result considering the maturity of the platform and the extension. So that's the only thing I can say.
Okay, thank you.
Thanks.
Okay, so thank you very much for your... Okay, the final talk of this session is titled Jasmine, Portable Multi-Language Data Analysis for the Web 25. Aaron, sorry.
Hello? Okay. Hi, I'm Aaron Munsters, a PhD student at the Vrije Universiteit Brussel, and today I'm presenting to you Jasmine, which is about providing a portable multi-language taint analysis for the web. And this work has been performed by Abel Stucker in the context of his third bachelor thesis. So before I get started, I would like to introduce to you an example of a JavaScript program. So here you can see a JavaScript function replace, which has the goal of to, given a text, replace a certain pattern by certain replacement, and then return the replaced text in which each occurrence of that pattern has been replaced. You could use that replace function, for example, to replace the template recipient with a runtime value, the recipient's name. And you could also to replace it in an email, or you could also, for example, replace the template timestamp to replace the current time in a certain log statement. Now, given that this is a WebAssembly session, you can also use that function replace as an import from a WebAssembly file. So someone has then developed that replace function in WebAssembly, compile it in a higher level language, C, C++, or Rust, compile it to WebAssembly, and then you can still reuse that same functionality. But let's say, or let's imagine that that replace function is a little buggy. Sometimes it might reuse arguments from the previous call in the next call. So it could be that that recipient's name might end up in the log statement, and that recipient's name might be in control of some user who is a little hacky and try to inject an SQL statement to essentially drop the table employees, and eventually that log statement might end up in some database and you lost all your data. Well, it's quite crucial to sometimes understand the WebAssembly programs, their behavior, and it's not always easily to do so. WebAssembly programs, they typically are included as they come from third-party vendors. They might be fetched over an insecure network, and within a single program, you might mix and match secure and insecure input and give it to a WebAssembly, one of those WebAssembly instances. Now, if you check the news lately, you can see that actually NPM has been an attack surface for supply chain attacks, and that both JavaScript and WebAssembly programs, where they interoperate, have been actually the target for such attacks. Now, in a more broad sense, we would like to, for interoperating programs between JavaScript and WebAssembly, researchers and developers might want to better understand the runtime behavior and the data flows of the programs under varying conditions for detecting undesired, unsafe, or malicious behavior, to perhaps analyze malware or to debug applications. And one way to do so is through a dynamic taint analysis, which is to monitor data flows through a program at runtime by labeling data with taint. And so there's 3 key phases. First of which is to mark taint sources in your program, there where values originate. And so throughout this presentation, I will use U to denote an untainted value, considered secure or irrelevant. And then T for tainted values, which is critical information that enters a program. Then in the second phase, the program is executing, and through taint propagation rules, the taint will be kept track of throughout your entire program. And eventually you can mark sinks in your program through which you want tainted values not to flow. Otherwise, your tainted analysis should report that something's wrong, that a tainted value reached a sink. And to couple back to the earlier example, you could, for example, mark the recipient's name to be a tainted value, and you could say that before you write something into the database store, you could mark the value that is being passed to the store as a sink, or that it's now about to reach a sink. So ideally, this program would panic from the taint analysis point of view. In the context of taint analysis, you define your taint propagation rules, and either they are available and correct, for which you can then consider your taint analysis to be precise, but if they are missing or incorrect, the analysis is imprecise. And then you have 2 cases, one of which is that you overtaint values, that is, you mark a value of tainted, whereas in reality it should have been untainted, for example, passing a safe string to the database, but the analysis panics. Or you have undertainting, in which you have a value that is marked as untainted, but in reality it should have been marked tainted. You pass some dangerous string to the database, but the analysis does not notice. And so we state that there's a lack of taint analysis precision for multi-language applications. That is, with current state-of-the-art dynamically analyzing JavaScript and WebAssembly interoperating programs, the analysis will either undertaint or overtaint, as you have no way of tracking taint for such interoperating programs. So we developed JASMaint, which is a multi-language taint analysis, and we wanted it to be portable. But before we built JASMaint, we first individually developed a dynamic taint analysis for JavaScript, another dynamic taint analysis for WebAssembly, and then we provided an orchestrator to essentially combine the 2 taint analysis to reason about multi-language applications. And one also key aspect of our implementation is that we wanted it to be portable. So essentially to have that analysis be deployed in multiple contexts wherever that JavaScript and WebAssembly programs can interoperate. So what I will show next applies to both the JavaScript and WebAssembly taint analysis. In terms of their portability, how we achieve portability is through using source code transformation. So for both languages, we will use an instrumentation platform that takes in any target program that we provide essentially an analysis, and then that instrumentation platform will rewrite the target program, inject the analysis, provide you a new target program that you can then execute, and then from that running process, understand its behavior. So in this context, the target program will be rewritten to inject taint tracking analysis, and then the idea is that that program can be deployed in these different contexts, server-side, client-side, or in the cloud. Great. So regarding the roadmap, let's dive into the details of the JavaScript taint analysis. So to develop the taint analysis for JavaScript, we use the frameworks Aran and Linvale as a source code instrumentation platform, and we essentially use a shadow values to track taint. So for example, on the right-hand side, you can see an uninstrumented program which would have the value foo. Well, the shadow value representation of the value foo would be essentially an object that has an inner field, which is still that value, but that object is then, with our taint analysis implementation, also augmented with a __ taint field, in which we essentially can keep track of the taint of that value. And besides the using shadow values, we also had to account for taint propagation. And so we provided taint propagation rules for intrinsic functions, which are functions provided by the VM, such as, for example, the join function that you can call on arrays. And then the source code instrumentation platform will handle user-defined functions as the composition of calls to VM provided functions. And furthermore, we also accounted for control flow taint. So that is based on control flow wherever your program flows, what dictates that control flow will also account for or will also taint values that based on control flow statements are now assigned new values. In terms of our API, you can mark sources using taint.source, sinks taint.sync. You can sanitize values using a sanitize function, which is to remove the taint from a tainted value in a sense that you can consider now a tainted value to be untainted. And we also can assert on taints using assert is tainted or assert is not tainted. In terms of our WebAssembly implementation, we also used a instrumentation framework, which is called Wastrumentation, as our source code instrumentation platform. So that rewrites a WebAssembly program into an instrumented WebAssembly program with the taint analysis. And we forked a shadow runtime framework, which we call WasShadow. And WasShadow itself precisely follows the WebAssembly semantics to trace values, shadow values of a WebAssembly runtime. So the analysis sort of mimics the runtime semantics. And we changed the tracking domain of WasShadow from WebAssembly values to now taint values. So think of it in the implementation that, for example, any entry that previously in the shadow runtime you were pushing on a stack, if it were a WebAssembly value, now we change that into being a shadow value with a taint status. Now, in more detail, so the shadow values, they track taint at a byte level. So a byte level can then be marked tainted or untainted. And so for 32-bit sized values, that means 4 taints. For 64-bit values, that means keeping track of 8 taints. And then the shadow stack and the shadow global store also continue to compute the taint of the values flowing through the program. And also for the shadow memory, it could be that you are storing tainted and untainted values into memory, which we then keep track of. So for example, in those 2 earlier instructions, the first is tainted, the second i32-bit value is untainted. And if you would then read from linear memory at a slight offset, we keep track of how that taint flows then also through linear memory. A little advertisement, I will be explaining more how Shadow works, what Shadow works in terms of its implementation and use cases during the WebAssembly workshop on Thursday. So feel free to join if you're interested. So next on is the orchestration between the 2 individual Shadow analyses or taint analyses and the interoperation between JavaScript and WebAssembly programs. And so we focus on 3 boundaries in which JavaScript and WebAssembly programs interoperate: function calls, linear memory, and shared globals. And for our implementation, we ensure that the JavaScript analysis side manages taint communication across the interoperability boundaries, and that the WebAssembly side only exposes the taint communication or only provides its API to read from the taint. And so this is essential, or this architecture is because we consider JavaScript always to be the entry point of a taint analysis. So JavaScript can call into WebAssembly to retrieve a result. JavaScript can call into WebAssembly, which calls back into JavaScript, but JavaScript was the entry point. But we do not consider an architecture where WebAssembly is the entry point of a program to start an invocation, and that is why the WebAssembly end only needs to communicate taint, but that the taint management is performed at the JavaScript side. So let's say that we have a function call in JavaScript. It calls into WebAssembly. On the WebAssembly end, it performs a function execution, and eventually it returns the result. Well, the orchestrator, before that function call takes place, shares the taint of the arguments. Then, during the execution at the WebAssembly side, taint is propagated, and eventually the taint of the result is also stored on the WebAssembly side. Then, when the function call returns, before the callee of that JavaScript function gets its result, the taint is retrieved at the WebAssembly side and also passed on when the JavaScript function then eventually returns. There are more details on the semantics of how the orchestration works, which you can find in the paper. Now, in terms of evaluation, we posed 4 research questions, which is, what's the runtime performance overhead for JavaScript taint analysis? What's the runtime performance overhead for WebAssembly taint analysis? What's the runtime performance overhead for JASMaint when we combine the two? And what's the taint tracking precision improvement for JASMaint? So in terms of evaluation, we departed from a multi-language taint analysis that has been developed benchmark suite, Truffle Taint, that covers 10 programs, and we adapted that input program suite to also conform with control-flow-based taint assertions, as that earlier work did not support it yet. And so to answer the first 3 research questions, we measured the performance overhead, and we measured the slowdown with respect to the baseline performance, so an uninstrumented program, for 3 key factors. So first of all, for the forward analysis, which we denote as an empty analysis. So you instrument the program, but do not account for any analysis semantics. Then for the shadow analysis, so this is a heavyweight analysis in which you keep track of all values, but do not yet keep track of all taint. And lastly, the shadow analysis with keeping track of the taint of all the values and also accounting for the taint propagation rules. So we did that for 10 programs, and you can see the results here. Note lower is better, and the information is on a logarithmic scale. So first of all, sort of a sanity check. Increasing complexity of the logic, you can see that always there's this upward trend. The more costly the analysis becomes, the more cost you start to pay at runtime. So this checks out. Then we also summarize the entire result of the execution slowdown of a JavaScript-only analysis is 1.72 to 12,000 times. For WebAssembly, it's 250 times to 1,200 times. And for the JASMaint, the runtime overhead is 11.93 to 2,500 times. So this is really costly. It does incur costly overheads. However, this is within the expected range for portable source code instrumentation. Then we also wanted to evaluate the precision, and so the methodology is to reuse that same benchmark suite. And so what we then do is we trace the execution of an entire program. So at any program statement, we record all the values. And what we wanted to compare JASMaint with is a dynamic taint analysis that could not keep track of taint at the WebAssembly side. So we called that the state-of-the-art taint analysis before we developed JASMaint. And its interoperation semantics is essentially, as long as the JavaScript side provides untainted values to WebAssembly, any value that is returned is also considered untainted. As soon as a tainted value flows into WebAssembly, since that WebAssembly module is stateful, we should consider any value that then is returned to be tainted. Then we compared this entire trace also with JASMaint's implementation, and what you can see is that on the top you have a correct implementation where the true situation, either tainted or untainted, is that both JASMaint and the SOTA implementation return the same result. However, it could be that the SOTA and JASMaint mismatch, and we consider JASMaint as the ground truth, since it can now accurately track the taint also on the WebAssembly side. So we consider those situations to report a false taint information, either that it should have been tainted, or that it falsely is marked as tainted, or falsely is marked as untainted. And so then to measure the precision improvement, what we do is we essentially see, okay, how much can JASMaint reduce the total information to just the true information that only JASMaint will provide. So what's there? The fraction, which is a similarity score, and based on our evaluation, the similarity score varies in between the different programs So we could reduce the overtaint down to 44% in the best case for Van-Kuch Redux. However, depending on the semantics of the program, there is less and perhaps less gain in that reduction. So this is, again, the overview. We provide Jasmine, a portable multi-language taint analysis for WebAssembly and JavaScript interoperating programs. And then we discussed, or we evaluated the runtime overhead for each individual component, and also measured how much the precision improves with Jasmine. Thank you.
Thank you very much. Okay, so it's time for question.
Hello. You said that you've looked at interoperation via memory, globals, and function calls, right? Do you know, like, why did you not look at table mutation?
So the instrumentation framework that we use is instrumentation, and it currently does not support tables. So there are plans to add that to instrumentation, then also add it to the taint analysis, and then we have a more program whole overview. But we did note that for our implementation, table manipulation was not used. So that additional semantics that we could keep track of does not influence these results.
Oh, I more meant not table mutation in WebAssembly, but table mutation via JavaScript.
We do. So at the JavaScript side, every semantics that JavaScript used as part of these benchmark suites, we also accounted for the taint propagation there. So all primitive data structures, including VM provided such as arrays, are also being kept track of.
Why does the slowdown for JavaScript span 5 orders of magnitude, and for WebAssembly it's less than 1 order of magnitude?
So this corresponds with the overhead expected from the instrumentation frameworks. So using Aran, or in the paper that describes Aran and presents Aran, also the execution overhead, the slowdown is within that same range for different dynamic analysis. And for the instrumentation paper, indeed, also the slowdown for different dynamic analysis is reduced. So it sort of corresponds with the instrumentation frameworks, but it aligns with our expectations. But exactly why it is so slow depends probably on the optimization opportunities to optimize the way that the tactics used to instrument these programs. So on the Aran side, certain metaprogramming techniques are used to inject the analysis in JavaScript. These could be harder to optimize for the execution engine, perhaps in comparison to the way that instrumentation does it, which is inlining analysis instructions in the target program. So that could be the reason why the overhead on the JavaScript side is so much larger.
Welcome back to this session in the afternoon. This session starts with a keynote speech. So I introduce the keynote speaker. It's my pleasure to introduce Professor Hideshiko Masuhara of the Institute of Science Tokyo, formerly known as Tokyo Tech. He has made an outstanding contribution to programming language design and programming environment. His work includes aspect-oriented languages, context-oriented languages, and meta-compilers. So please start.
Thank you. Thank you for nice introduction, Uga-san. And it's very honor to give a talk here. And I changed the title of my talk as a joy of tracing just-in-time compilation more than just a JIT compiler generator. Because when I prepared my talk, I wasn't sure what I'm going to talk, but in the end, I realized that this is something about making the meta-tracing just-in-time compilation to do more than compilation. And I think I'm given 40 minutes for this, including questions and answers. So I guess it's better to accept the questions in the middle of the talk. So if you have any questions, then please feel interrupt me. And sorry for online guys. And this talk is mainly about the work jointly done with Yusuke Izawa, Carl Friedrich Boltz, and Yusei Yoshimura and Yudai Tanabe. And let me start with very short introduction about the meta-JIT compilers and also partial evaluation, also known as the Futamura projection. Introduction to partial evaluation in 1 minute. So partial evaluation is a program transformation technique by providing a partial input to the program. And usually, for example, can I show a pointer? Okay. So let's assume this program that computes the typical program that computes the nth power of x. And we specify the partial evaluator. We are going to give only input n. So then usually partial evaluator analyzes the program which depends on the n and which doesn't depend on or depends on x. And this red box part is depending on the value of x, which we call dynamic code. And then given a static input, which means the n, for example, 5, then we execute the program for the only static part of the code. And emits the dynamic part of the code, and then we will get this kind of result. So the x times x times x times x times x times 1. This is partial evaluation. You understand everything. All clear. Okay. Then partial evaluation gets more interesting if we partially evaluate programs with respect to an interpreter. In my slide, I write eval for shortness, and because if we partially evaluate an interpreter with respect to the interpreted program, then we will get a compiled code. So this means the partial evaluator can compile programs. And let's also see by an example. Here's a code which is a tiny interpreter that interprets a bytecode program, which gets the code as a bytecode, sequence of bytecode, and the argument to the bytecode. And then this is just typically interprets the fetch instruction, interpret if it's multiplication, then manipulates stacks, and then advances, manipulates the stack pointers, program counter, and so on. And if we specify this is, we only want to partially evaluate the code input, and then those red part is dynamic part, then if we provide the source code, which is a bytecode sequence, then we will get this kind of compiled code, which only consists of the manipulation of stacks, and there are no code that manipulates this code parameter. So in that sense, this partial evaluator compiles from this source code into that compiled code. Okay, so introduction is over. Now, next introduction is about the meta-JIT compiler frameworks. Famous things are known as the R-Python or PyPy and GraalTruffle. And those frameworks can generate a virtual machine from interpreter description. So, for example, if we write an interpreter of JavaScript and put that interpreter description into the R-Python framework, then we will get a JavaScript virtual machine for JavaScript virtual machine. So this is very nice because if we can only write different interpreters of different languages, we will get the virtual machines of different languages. So so RPython and GraalTruffle are successful of generating the virtual machines for Python, JavaScript, Ruby, Smalltalk, or even for LLVM. And if we look inside of the virtual machine, then we can consider this virtual machine consisting of the two parts. One is interpreter part, which is just a compiled code of the eval, and also the just-in-time compiler for L. And this interpreter basically executes the program and find hotspot, and then run the just-in-time compiler to get the compiled code. So then if we look this figure, then we see that this framework gets interpreter and do compilation. So this looks like doing some kind of Tamura projection. But I was actually not sure. And actually, this is a quote from the paper written by Carl Friedrich, both in original PyPy's paper. Then it says, conceptually, there are some similarities in partial version to PyPy work. So he wasn't sure. And actually, I was asked by Carl Friedrich around this time whether what he was doing is partial evaluation of Tamura projection or not. And at that time, I couldn't answer. Maybe similar, but I am not sure. But now I think I can answer this. But in order to answer to that, I need to explain in more detail about the meta-tracing JIT compilation mechanisms. In specifically what RPython does. So from now on, I'm only going to talk about the meta-tracing JIT compilation, so based on RPython framework. And then again, RPython takes interpreter or any kind of program written in RPython. In this case, we use same bytecode interpreter. And then RPython first compiles this interpreter into C program. So this is an intermediate code that RPython compiles. And I'm only showing this handler part, this part which handles the multiplication instructions. And you don't need to understand this code, but this is basically just a compiled code. And then we specify which part of the input is static and dynamic. Again, this red part is dynamic part. And then what next thing to do is to run the program. And in this case, we provide both static and dynamic input. So the static part is bytecode instruction set, and the instruction stream, and the dynamic part is some argument to this interpreter. Then the partial RPython or the framework actually executes this program and then creates a trace of execution. And trace is a series of instructions that was actually executed on particular run. And then in this case, for example, in the middle of this code, there's a multiplication instruction. So inside of the trace, it also contains the trace of the executed instructions, and also the values used for execution. So those green and red values are actually we observed during the execution. And then what's the next thing to do is to remove static code, which means the instructions depends on the only green values, and then also embed, then we will only see those 4 instructions, and then embed the static values into the instructions, and then compiles those intermediate code into the native code. That's the basic idea of the RPython's meta tracing JIT compilation. Is this clear to you? Okay, then by explaining this, I can now clearly say that this is the first Futamura projection. And the relationship or difference from the original Futamura projection or partial evaluation to this tracing JIT can be explained in this way. So the partial evaluation partially evaluates static code and emits dynamic code. So it only executes static code. Whereas the tracing JIT actually fully execute the program while and also fully emits the code. So both static and dynamic parts are executed, and both static part and dynamic part are produced as an output. Afterwards, from the emitted code, which means trace, we remove the static part of code, we will get the partially evaluated code. So it looks slightly differently, but effectively both are doing the same. So I hope you are you agree with me. Okay, then introduction is over, and then what are interesting part. So the real part begins from now. So then what I want to show you is, what I have shown you is a meta tracing JIT compiler can compile programs. So it generates the JIT compilers, but it can do more than that. So as I have shown, if we give the language semantics as an interpreter, then the meta JIT framework can generate the JIT compilers. But if we specify something different, like code traversal, so not just the language semantics, but something what compilers do, then we will get some interesting behavior of the virtual machines, like a method compilation, threaded code generation, or even more, we can do some kind of optimizations like inline caching and the multi-tier compilations. I'm going to explain one by one. So method compilation. By the way, I haven't explained explicitly, but the meta tracing JIT compilers is a tracing compiler, which means if there is a conditional branch, then it compiles only one branch actually executed. And the method compilation is usually compiles the whole methods. That means if there is a conditional branch, then it compiles both then and else branches. So then by tweaking the meta interpreter definition, we can get the method compilation by using the R-Python framework. Let's see how we can do that by actually changing the semantics of branch. So here is a semantics of branch instruction, condition jump if 0, and which is basically checks this top of stack is 0, and if it is 0, then then update the program counter to the jump target, which is very simple and very clear to you, I hope. And if we change this semantics into this way, so that the first emit the if instruction, and then recursively calls the interpreter from the next instruction. That means we just use some trick to generate the direct code directly. So we emit if instruction, and then next thing is generate from the else part, and then generate a label, and then continue execution or evaluation or compilation of the jump target. So this is an interpreter definition, but it also looks like a compiler definition of if then else statement. Compile then else part, or generate if instruction, compile else part, generate label, compile then part. And if we provide this interpreter definition into the R-Python framework, then we will get the method compilation so that we can get the both then and else branches. And of course, this is not as easy as explained on this slide, so we need to do more on the dark side, but I don't have enough time to explain that. If you are interested in, then I can explain later. Anyway, so then, but this is an interesting combination of the interpreted semantics and the compiled semantics, but we could get something very interesting. Okay, then next thing is threaded code generation. Threaded code is a very old technique, almost 50 years old techniques to generate kind of a quick compilation mechanism by generating a sequence of handlers. So for example, if we have this kind of source code, then the threaded code generation basically generates the call of the handlers of each corresponding instructions, and which was done by manually making some translators. But I'm going to show this is also possible, automatically enabled by just tweaking meta interpreter. And for example, if we have this kind of interpreter definition, then the R-Python framework usually generates the compile code in like that. So this is what I have shown as a compilation. But we just add some annotation, don't look inside, which is R-Python's special directive, not to trace this side, but leave just a call to this handler. And then we will get this trace, which is actually looks like, and which is actually a trace threaded code. So this is also very interesting. So just one interpreter definition, we can do a full compilation or threaded code generation. And there are also many some dark side to realize this, but let's move on. So the next thing is inline caching. And inline caching is also an old technique to optimize the indirect call by replacing with direct call when it is calling to the same target, which is usually done for the object-oriented programming for method dispatching. So if we do the method dispatching on the same class, then we just insert the direct call to the method body by just checking the class of the target. And for example, if we have without inline caching, if we have semantics of the function call, in this case, I'm going to simplify the function call of the not object-oriented, but the first-class function call, then its semantics is basically going to be get a function object from the stack, and then the evaluate based on evaluates that function by using the interpreter call. But in this case, the function is dynamic value, so we have no way to compile. So by using our Python, we can get this is going to be compiled into a code, just performs the interpreter call. Inside of the interpreter call, it's just going to dispatch to the just-in-time compiled code. So this is basically, you can understand this is going to be compiled into an indirect branch, indirect jump. And but by using one kind of our Python feature just to generate the direct call and also insert some kind of cache technique. So for the first time, we record the last time. So we record for each call site which function was called, and the next time the call happens, if we are going to call the same function, then we generate a direct call. This is also an interpreter definition. So if we just interpret execution, it does exactly the same the original execution just by checking the recording and checking. But if our Python actually traces and compiles, then we get this code. So for this part, so when tracing compile happens, then it comes into here, which is compiled into guard instruction, and then it generates the call instruction. And then if we look this code, then it exactly the same as the inline caching code. So the first checks the call target was what we actually recorded before, and then directly call the target. Okay, the last thing, which is multi-tier JIT compilation, and which is found in many modern just-in-time compiler virtual machines, which is using the multiple just-in-time compilers. A lower tier is fast, but it produces low-quality code. And the higher tier compilers takes more time to compile, but it generates the optimized code in order to balance between the startup performance and peak performance. And with our Python framework, since our Python actually generates the compiled code based on the interpreter definition, so it can be easily done in principle by providing the different interpreters our Python frameworks. We will get the different compiled code. So multi-tier JIT compilation seems to be easy, but really interesting or really challenging part is how to switch those interpreters within our Python framework. And in order to do that, we found that when we actually implement a user-level profiling, then we can do the switching the interpreters, which means for example, this is a semantics of the conditional jump instruction, And this is a original definition of the conditional jump, which does nothing, just conditional jump. And and assume this code is written as a lower tier interpreter. Then we insert tracing profiling code like this way. So just count up the execution times for each program counter, and the counter reaches to the threshold. Then let the higher level, higher tiers interpreter evaluate the rest of the program. And then the Python framework automatically compiles with respect to the compiles the higher tier interpreter, which produces which takes more time, but it produces the faster code. Then we realize the multi-tier compilation. And I'm not going to read this dark side, but there are many techniques to realize that. But putting those things together, we actually enable to implement it two-level SOM, simple object machine, which is a subset of Smalltalk, and like in this figure. So this blue box is original SOM implementation, which was around 16 kilolines of code, and we added the first tier evaluation, which implemented the threaded code generation and also method traversal mechanism. And then we also made a driver evaluator, which basically delegates everything to the first tier interpreter, and then we will get the threaded code here, in which we have a user-level profiling mechanism also, and also inline caching mechanism in order to recover some performance loss of the threaded code. Then this user-level profiler actually triggers the tracing next level of interpreter, which is original tracing compiler, which we get the faster code. So this is, in the end, this is something similar to the multi-tier virtual machines in these days. And the result is very satisfactory or surprising to us. So we implemented two SOM and compared to performance the original Python with respect to a large application, then measured the startup performance. Then we found that our implementation actually improves by 15%, which is very nice. And we also lose some performance due to the multi-tier execution, and we found we got roughly 5% peak performance overhead. Okay, so what I've shown was so meta tracing JIT compilation framework is not just a JIT generator for different languages. That means it can generate the JIT compilers, but we now see by adding something, I don't find any good word but for here, but add something, then we can provide many different behaviors of virtual machine. So beyond the compilers do. So I could say we knew that the partial evaluation of language semantics do compilation, but we also knew that the partial evaluation of virtual machine behaviors, we get something beyond compilation. And I also don't know good word for here, but something interesting. And I only have 10 minutes. Okay, so next part is going to be very quick. Maybe just it's ongoing work, but another interesting use of tracing JIT compiler is an easy backend of multi-stage programming, and I'm going to skip. So what multi-stage programming is, I don't need to talk about this one, but multi-stage programming is just a manual partial evaluation by specifying this part is dynamic code, this part is static code, and code in those boxes. And the notable implementations are the meta OCaml and the Scala LMS. But if we wrote an interpreter in meta OCaml and the generator compiled code with a factorial program of that simple interpreter program, and they executed that program for factorial function for 50,000 times, then we found that this performance. So this is interpreted execution. This is meta OCaml dynamically compiled execution. Then the compiled code is very fast, 20 times faster than original one, but it takes the 80 milliseconds of compilation dynamic code generation, which is sad because the meta OCaml actually uses a ahead of time compiler behind the scene. And that means even if the first stage it generates the AST-like code, it converts into string, and then the full compilation happens here, like parsing, type checking, code generation, and so on. So obvious optimization is to generate the AST or even generate the intermediate code during the first stage computation, but which is very heavy. Which is as heavy as hard as we are making another just-in-time compiler. So what we found is just use the lambda closures without modifying the underlying language mechanism. So given this multi-stage program, we propose to convert this program into this program just generates the lambda expressions. So for example, for this part of the code, it just generates a lambda closure that computes the x times the generated code. And then if we provide partially evaluate this function, then we will get this chain of closures, which isn't usually fast because the number of the indirect calls. But by using tracing JIT compiler, this chain of closures is optimized away. And then what we found is that another experiment. Unfortunately there is no tracing JIT compiler for OCaml, so we use PyPy for the comparison. And then PyPy is not as fast as OCaml if we execute it by interpreters, but with the lambda staging, so by using lambda closures, then we will get this performance, which is actually faster than the meta OCaml. So which is kind of nice. So from there, I found that we often want to generate code, even at runtime. So because that's why many languages have macros, template metaprogramming, or evals, or multi-stage programming. And it seems that the lambda closures and the tracing JIT may achieve both good code generation speed and and the generated code speed. So it might be a very nice place to play with for code generator backend. So then this is the last slide. So I'm going to summarize my messy talk. And so I first showed that the meta-JIT compiler framework can implement VM behaviors beyond compilers. So there should be many interesting future work, like implementing more virtual machine behaviors, like special optimization techniques, and the language-specific, application-specific optimization techniques. And also, I'm very interested in making a kind of toolkit for defining those kind of interpreters. And second part is about the tracing compilers can be a good backend for dynamic code generation. And maybe it might be interesting to generate a series of multi-stage languages based on the meta tracing JIT compiler framework. And what I haven't, I'm only talked about the RPython, but the GraalTruffle is another meta JIT compilation framework, and we can also think about the same kind of things based on the GraalTruffle. So that's it of my talk, and thank you for listening, and I'm very happy to get questions.
Very complex things very unmessy, so thanks for it. I'm Manas Thakur from IIT Bombay. The question I have is, you talked about a subset of Smalltalk. So are there features of Smalltalk or language features in general for which generating multi-tier JITs like this is difficult?
So your question is basically about the difference between SOM and Smalltalk.
Or in general.
Or in general. I don't have a good answer right now. Stefan is here. maybe he can he can answer after the session. But yeah.
We'll talk later.
May I ask a question about threaded code? You introduced several techniques that can be achieved by meta-JIT compilation. For this threaded code, is this actually benefit for developing virtual machine? Is there any benefit compared to compiling into the native code?
Oh, I see. I was very bad to talk about, but the threaded code is basically good for faster compilation. And so compared to the, maybe this one. So for the backend of our Python, compiling this trace takes much longer than the compiling this trace. So by using threaded code generation, we shorten the compilation time, which actually benefit for the startup performance. That was the...
yeah, thank you. So this contribute to the multi-stage compilation?
Yes.
Thank you. Other questions? Or some comments from Stefan?
I was asked about the difference between SOM and full set of Smalltalk.
Questions?
Thank you for the talk. So I study multi-stage computing, so the latter part was really interesting. So speaking about the latter part so applying meta tracing JIT for multi-stage computing, so you said code generation is translated in function in Python. So does it mean that this staging is basically assumed for runtime? So how can I say? So it's basically online code generation where generated code is evaluated at the same stage.
I guess the question is about the.
My question could be: so the code generated power function will be evaluated at the same time, or is so the generated code can be output
I see. So
code and then evaluated in another
the
stage.
question is about whether this is assuming the offline code generation or online code generation.
Yes, exactly.
I'm assuming online code generation. So for example, this time the 5 is static input, but sometimes the file is provided by from the user or at runtime, and then generates the power of 5, then the executes that function at the same time.
I see, I see, I see. Yeah, thank you very much.
Okay. Okay, so let's thank to the speaker again. Okay, in this session we have 3 more talks, so I see.
a minute or so before we get started. I do want to start on time so that if are we broadcasting this live? Yes. Okay. So
I got a message that the Zoom link was not working.
the Zoom link is not working.
Was not working.
Oh, I see. So there was a request not to record the previous talk. Okay. There we go. So just leading into this, I would like to introduce the next speaker, who is Go Suzuki, speaking on cooperative JIT compilation for resource-constrained low-power coprocessors. And you can get started when you're ready.
Okay. Thank you for the introduction. This is Go Suzuki from Institute of Science Tokyo. This talk is a continuation of our work in progress paper presented in the last year's MPLR. Recent microcontrollers have powerful processors and memory resources to meet the requirements for IoT applications. However, such powerful resource costs higher power consumption. Therefore, modern IoT SoCs like the ESP32C6 are equipped with a low-power coprocessor or LP coprocessor. It is there to handle simple and long-running tasks on behalf of the main processor. The LP coprocessor can significantly reduce overall power consumption. However, this power efficiency comes with limitations. For example, the LP coprocessor cannot access high-speed peripherals like SPI. More importantly, it has access only to a limited amount of the memory. On the ESP32C6, only 16 kilobytes of memory is available when the main processor is asleep. These constraints introduce several major programming challenges. First, our target LP coprocessor has no memory protection unit. This means that memory safety is not guaranteed by hardware. On the ESP32C6, accessing an invalid pointer can result in corrupted data or even freeze the LP coprocessor. Second, as shown on the previous slide, the LP coprocessor cannot access the main memory. So developers must manually transfer all necessary data between processors. Third, available memory for code is extremely limited, just 16 kilobytes in our case. This means we must be very selective about the code we place on the LP coprocessor. Finally, the processors can have different ISAs. This is often a deliberate design choice to optimize one core for performance and the other core for low power. However, this increases development effort. For instance, with the ESP32 SDK, a developer needs to write two separate main functions and manage two sets of source code. These are the key challenges we address in this work. To solve the first two issues, memory safety and separated memory spaces, our managed runtime system takes responsibility. It automatically checks pointer validity and moves objects as needed. This frees the developer from manual and error-prone memory management. Second, to tackle the problems of limited memory and different ISAs, we use JIT compilation. The key idea is to generate only the code that is actually executed, ensuring a small footprint and resolving ISA differences on the fly. So in this talk, I'll introduce our solution to these problems. Our goal is to make it practical to use manageable languages on LP coprocessors, with focusing on common IoT use cases like sensing and buffering tasks. Our key idea is a cooperative JIT comparison. In our approach, the powerful main processor handles comparison for the LP coprocessor. It traces the application and comparing only the necessary parts into a highly specialized native code. Then I will also briefly touch on our object management system, and I will show experimental results from our prototype on the ESP32C6. The generated code is larger than C, but the power saving is comparable. Finally, I'll discuss about other languages and related work. Here's an example. This Ruby code reads from a sensor in a loop. With our system, a developer can offload this entire loop into the LP coprocessor with a single copro.run call. This high-level approach has several benefits. For example, object-oriented features simplify the abstractions of different hardware sensors. More importantly, our runtime automatically handles the transfer of necessary objects, like the sensor and result objects. It ensures they are safely accessed on the LP coprocessor. To design our system effectively, we first considered what tasks are best suited for LP coprocessors. Prior research shows that the most significant power savings come from offloading tasks that are simple and frequently executed, like sensor reading and data buffering. In contrast, computationally intensive tasks like signal processing offer only marginal gains, as they tend to run less frequently. Therefore, our experiment is designed for these simple and high-frequency tasks. So why did we choose just-in-time comparison? The main reason is to minimize the code footprint. Managed languages tend to produce large binaries. For example, dynamic dispatch requires Berkeley virtual function tables and introduced to resolve method calls at runtime. Dynamically typed languages are even more overhead with runtime type checks. A naive ahead of time compiler would have to include all possible code passes. It would quickly exceed the memory limits of the LP coprocessor. On the other hand, our JIT compiler allows us to compile only the code that is actually executed. It is suitable for this resource-constrained environment with limited memory. Now, let's dive into how our cooperative JIT works. The core idea is that the main processor and the LP coprocessor work together. The main processor compiles for the LP coprocessor. This aims to reuse the interpreter implementation on the main processor and to use the powerful main processor for the main compilation. I will now explain how JIT operates. This is an example of control flow graph. These cycles are basic blocks. Specifically, I will discuss the operation of copro.run, which is the method for offloading. When copro.run is called, its argument code block doesn't immediately execute on the LP coprocessor. Instead, it begins running in the interpreter on the main processor. As it runs, our runtime traces the execution path. It observes which basic blocks are executed and what data types are used. As the trace proceeds, the JIT compiler generates native machine code for the LP coprocessor. This process is inspired by trace-based JIT. Crucially, the generated code is specialized based on types and divided into basic blocks. Because we know the runtime types from tracing, we can eliminate dynamic type checks and resolve method calls directly. This part of our approach is inspired by lazy basic block versioning. When the execution reaches any compiled basic block, it is migrated to the LP coprocessor. The main processor wakes up the LP coprocessor and transforms the stack frames for the LP coprocessor. After the migration, the main processor sleeps and the LP coprocessor runs the compiled code. To reduce migration overhead, we migrate only when the execution reaches any compiled basic block. This differs from an original LBBV approach, where the execution would migrate every time each basic block is compiled. When the LP coprocessor encounters something unexpected, like an uncompiled branch or a variable with a different type than predicted, it jumps to a stub function. This stub function dumps registers to the stack and wakes up the main processor. The main processor then resumes and compiles the new code path and patches the jump to the stub function. Eventually, the execution is migrated again when the main processor reaches any compiled basic block. Next, let's talk about object management. To save memory, we use different object representations. On the main processor, we use a flexible dictionary-like format to support Ruby's dynamic features. But for the LP coprocessor, we convert objects into a compact and fixed layout format, much like a C struct. This saves a significant amount of memory and allows for simple access to instance variables. A key rule in our design is that any pointer on the LP stack has already been validated. This means its referenced object has been transferred and type checked. We enforce this invariant when transforming the stack and whenever reading non-local variables. This is because we gather types from the interpreter and use concrete types to simplify the implementation. The benefit of this approach is that we can eliminate checks on writing to instance variables. In addition, we assume that objects on the stack are likely to be used soon. Therefore, to reduce main processor wake-ups, our runtime moves these objects beforehand when transforming the stack. To evaluate our design, we implemented a prototype based on MRuby/C. we tested we tested for we tested 4 applications. These applications differ in their tasks and execution frequencies. The simple blinking LED toggles GPIO within a loop. The other 3 applications perform more complex tasks like sorting and averaging. We conducted the experiment with 4 configurations. RM is the original MRuby/C, which interprets Ruby on the main processor. RL is our modified MRuby/C, which JIT compiles Ruby programs on the main processor and run on the LP coprocessor. CM and CL are handwritten C implementations running on the main and LP coprocessors respectively. First, let's look at the generated code size. The green bars show the generated metadata size on the main processor. The blue bars show the generated code size on the LP coprocessor. The red line shows the code size ratio to handwritten C. As expected, our generated Ruby code size is larger than handwritten C. It is up to 6.6 times larger for the most complex tasks. This is the main trade-off of using a high-level language. However, it's important to look at the absolute values. Even the largest application required less than 2 kilobytes of code. This is well within the capacity of the LP coprocessor and demonstrates that our approach of compiling only what's needed is effective. Next, let's see the most important result per consumption. The chart on the left shows the power savings achieved by offloading to the LP coprocessors. The key takeaway here is that our approach in Ruby, in red bars, achieves power savings that are nearly identical to the handwritten C implementation in the blue bars. The difference is negligible. The chart on the right side shows the JIT overhead. We can see higher power consumption during the first few iterations because the system compiles code and moves objects. However, the system quickly stabilizes into its low power state. For any long-running IoT application, this initial one-time cost is easily amortized. Finally, let's look at the runtime size. The original MRuby/C runtime is over 40 kilobytes, which is far too large for the LP coprocessor. On the main processor, our modified interpreter is about 35% larger than the original, mainly due to the addition of the JIT compiler logic. Our runtime for the LP coprocessor, including the GCC and the stub function, is only 5.2 kilobytes, easily fitting within the 16 kilobytes memory. Finally, let's discuss how our cooperative design could be adapted to other languages. First, let's consider languages like C and Rust. A key challenge here is object management. Even though these languages don't have GCs, our system would still require runtime checks before every memory access. This is to handle the movement of objects between the main and LP memory spaces. Next, What about the statically typed languages like Java or C#? For these languages, a technique like lazy basic block versioning might be less critical because of fewer runtime checks. However, the fundamental challenge of object movement between separate memories would remain. Therefore, we believe that our approach of dynamically loading code and data is still a very feasible and beneficial approach even for these languages. There is related work targeting server systems or rich embedded systems such as Android. These three works are close to our work compared to systems like Reflex. Our approach is tailored for manager languages and doesn't require manual locking. Because Reflex assumes that the processors work simultaneously. So it serves software-based distributed shared memory, and developers need logs for shared objects. Unlike transkernel, we compile application bytecode on the main processor, not kernel binaries on the LP coprocessor, and performs specializations based on types. Sidewinder focuses to wake up main processors by an LP coprocessor. It lacks flexibility because they provide only predefined APIs and hardware. This makes it difficult to use various sensors. In conclusion, we have addressed the challenge of using high-level manager languages on resource-constrained low-power coprocessors. We proposed a cooperative compilation design where the main processor generates specialized compact code for the LP coprocessor. Our experiments shows that this approach makes it practical to gain the productivity and safety benefits of a managed language while achieving power savings that are comparable to C implementation. Thank you.
For questions.
How difficult is it to create such just-in-time compilers?
It takes one year and a half. So I think debugging garbage collector is more difficult than JIT compiler because
oh my gosh, thanks so much.
Yeah, because no memory protection unit.
Can you comment on the time it took to build those JIT compilers?
No.
So how much time was it? How much effort was it for you or your team to build the JIT compiler?
One and a half. 1.5 years.
How long was this lines of code you wrote for just-in-time
compiler? I will check later.
Okay. Answer offline. Always a good response. I'll talk to you offline. Best answer to the question.
Thank you.
Okay, so are there any further questions? Okay, if not, then let's... yes, here we have one. Okay, thank you.
thanks for the interesting talk. I remember that you mentioned you use like a tracing JIT compiler to generate code for the low-power coprocessor, right? But then my question is that what if, as you mentioned, like the MEM processor and the low-power coprocessor could have different architecture, then apparently tracing JIT won't work. So how do you solve this problem? Do you have some sort of like intermediate representation too?
In our implementation directly translates MRB bytecode to RISC-V, and the generation of code is performed by directly writes instructions by hand. Not like Python.
Okay, thanks. I got my answer.
I encourage you to continue the conversation afterwards, but we do have to move on to the next. So the next speaker here. Thank you. So this is a short talk now. We have a brief pause for video issues.
Just hold time.
We're getting it sorted for you. Okay, so we're good to go. So the next speaker is Yakavos Kolokasis, and he will be speaking about Smart Sweep and efficient space reclamation in tiered managed heaps.
Okay. Hello everyone, my name is Yakavos Kolokasis, and I'm going to present you our ongoing work, Smart Sweep, a system for efficient space reclamation in tiered managed heaps. Today, popular big data analytics such as Spark and Flink run on managed runtimes. These analytics demand to process a large amount of data sets, so they need large heaps for their computations. But scaling DRAM in a single server is costly and impractical. To overcome this problem, we can use remote memory by using idle memory across remote servers. This is a scalable and cost-effective solution to extend the Java heap today. However, the GC over remote memory is expensive. Let's say by having a large heap over remote memory, where this heap is on remote memory and you will use the local DRAM as a page cache. During the garbage collection and during the scans and compactions, there is a lot of network traffic as the collector needs to access remote objects. So our approach is to divide the heap into two subcomponents. We have a local heap in the local memory and a second larger heap over remote memory. This dual heap architecture gives us the opportunity to to cope with large GC costs by limiting the GC operations only in local memory. So no full scans and compactions over remote memory. In the paper, we show that such a design has the advantage to reduce the network traffic up to 177 times compared to a single heap approaches. Now the challenge is how to reclaim space in remote heap promptly. Otherwise, if we don't reclaim space promptly, we can result in out-of-memory errors because the remote memory is limited. Our approach is the Smart Sweep. It's a proposal for space reclamation in remote memory without GC scans. We use the two-heap architecture, and we have the local heap and the remote heap. And now the remote heap is a region-based, so we treat all objects as a single unit inside a region. Instead of scanning remote object, we estimate which object in H2 are alive. To do this efficiently, we use the metadata in the local server about each region. To reclaim now the dead object in H2, we transfer regions from the remote heap back to the first heap, and we allow the garbage collector to work locally and reclaim this object. So, and next, after we explain the problem statement and the overview of our solution, I'll present you the preliminary design and implementation of Smart Sweep, and at the end, I will show you some preliminary but promising results. The first challenge of our design is to find dead objects without scanning the remote heap. For this purpose, we have to estimate the live object for each H2 region. To do this, we track the forward references from the first heap to the second heap, is this with the red arrows. And also, we need to track the changes in the object references inside the regions. For example, an update if the object in the object reference indicate a creating of garbage. For the forward references now, we use a spatial information approach. We see that using a simple reference counting per region result in misleading results. For example, as you see in the figure, in the first region we have 2 pointers that results in object C, and in the second region we have again 2 pointers that results in 2 different objects in the second region. But we have 1 object here and 2 objects here. How we can distinguish these cases? For this region, we use a liveness byte map, where each byte of this byte map maps a 4K segment in H2. So we check where each forward reference lands in H2, and we mark the corresponding byte in this byte map. So now we have the information that 1 byte is active here and 2 bytes are active here. Next is for the inter-region references, we track the updates by the mutator threads. To do that, we use a card table for H2, where each byte maps again 4 kilobyte segments of H2, and we instrument the post-write barriers of the interpreter and the JIT compilers to record mutator updates. At the end of each marking phase, we count the number, for example, in here, and during the update of the mutator threads remove 1 references, and we have this information in the card table, and again it removes the other 2 references. We have again we track these updates in the card table. And at the end of the marking phase of the garbage collector, we can count the number of dirty cards that reveal changes in the object graph. After finding the live objects in H2, the challenge that we have to solve is how to reclaim dead object without compactions. For this purpose, we need first to score each H2 region. For the scoring purposes, we use the ratio of the number of dirty bytes in the liveness map to the number of objects in the region. Also, we use the number of the dirty cards per region. For example, in here we have one byte in the liveness byte map and 2 dirty cards. So this is better candidate to reclaim it. Then, after we do that, we need to define a threshold that help us to select which regions we are going to reclaim. To avoid in-place compactions, we select to transfer regions from H2, the objects in H2, back to H1. To do that, let's say we select, we move the object from this region back to H1, we update the reference, and in the next garbage collection cycle, the garbage collector is going to reclaim the and E object, and it's going to move the C object back to H2. For the regions that are fully of garbage, we just zero their metadata, and we have more information in the paper. The final challenge we have to solve is to maintain the cross-region and the cross-heap references to avoid runtime errors due to dangling pointers. An iFix is to move the region's entire transitive closure. However, this is expensive where dependencies are widespread in the whole H2. Another approach is to leverage the property of smart sweep placement strategy that puts at the transitive closure of an object into a separate region. This provides limited connectivity across region, and it's cheap to patch these references in place. However, for a future work, we want to try to maintain cross-region remember sets that we will update during garbage collection and during the JIT post-write barriers. Our preliminary implementation of Smart Sweep is that we implement Smart Sweep on top of TeraHeap. TeraHeap is the state-of-the-art dual heap architecture system in OpenJDK 17. We organize objects into region and reclaim, the TeraHeap organize objects into region and reclaim entire regions where objects are dead. This is suitable for large and low-cost capacity storage devices, but it's impractical for limited remote memory and results in out-of-memory error. Our prototype now moves to H2 only primitive types and leaf objects, and there are only forward references from H1 to H2. These primitive and leaf objects for big data workloads occupied more than 70% of the Java heap, as we see in Spark and Neo4j, and confirms that our prototype captures the dominant memory behavior. Also, we set Smart Sweep to access remote memory via NVMe OF and use memory mapped.io. For our experimental setup, we use 3 servers, one server to run the application and the other 2 servers act as remote memory. And we run Spark with 8 mutator threads and Neo4j Graph Data Science, the community version which supports only 4 mutator threads. And we run in all setups with 8 GC threads. As you see in here, we evaluate Smart Sweep compared to TeraHeap using linear regression, logistic regression, SVD++ and triangle counts in Spark, and SynDLP in Neo4j Graph Data Science. We see that across the execution, Smart Sweep achieves comparable performance with TeraHeap, that TeraHeap do not reclaim space promptly and waits to reclaim entire regions of garbage objects. However, the good point of Smart Sweep is that it can reduce the space waste by 50%, as we see in this experiment here, where we show the H2 garbage objects before and after each garbage collection cycle. Next, we evaluate how sensible is having a static threshold. By using, in here, in this experiment, we use 4 different thresholds, low value threshold and high value thresholds. And in here, we have the performance breakdown by showing the mutator thread execution time, the major GC time, and the minor GC time. And here is the performance of TeraHeap. By having a small threshold means we move to H2, from H2 to H1, more region that contains garbage instead of live objects, okay? And we see it here. And the performance, it's comparable with TeraHeap. If we have a larger threshold, we transfer from H2 to H1 more regions that contains more live objects, okay? And these put pressure in H1 in the garbage collector, and we show this pressure mainly in the major garbage collection time and also in the in the minor GC time, because the garbage collection cycle becomes more frequent and the garbage collector cannot reclaim enough space. To conclude and to show you the future work, we show that to deal with large GC cost over remote managed heaps, you need to use a dual heap approach. The problem in the dual heap approach is how to reclaim memory promptly. We show Smart Sweep. Smart Sweep shows how to reclaim dead objects in remote memory without scanning the remote heap by estimating the amount of garbage and move regions with large amount of dead objects from the second heap back to the local heap in DRAM and allowing locally the garbage collector to reclaim this object. Smart Sweep cuts the wait space by half and stays as just as teraheap. For future work, we want to extend Smart Sweep to support transfer to H2 object with references and supports a dynamic threshold for selecting which regions to move from H2 to H1. Then we want also to extend the evaluation by using CXL and also show what happens with compressed DRAM setups. Thank you for your attention. I'll be happy to answer your questions.
I have a question.
Okay.
I always have to have a question when there's no question from the floor. So you mentioned, of course, that your prototype doesn't deal with the references in the remote heap. Do your workloads really need that?
Well, because, for example, if we use, we don't know how these workloads, these big data workloads will change in the future. So a more complete solution should have also this support. And also, if we support the object with references, we might find also other cases beyond big data frameworks that we can use.
Okay, so you're preparing to be more general than the specific workloads that you have at hand, is that right? Yeah, okay. All right, thank you. Any other questions? Otherwise, we can adjourn for coffee or tea or whatever your preference might be. So let's thank the speaker one more time.
Thank you very much.
very low.
Good. Yes.
Still power source here, because I'm running low.
What would you like? Some power?
Some power.
Oh dear. That's a bit unfortunate. Presumably power must come from down here.
I hope my
That's
battery
the gangs.
can finish.
This is a bit rubbish, isn't it? Power bit.
No power source. We're just trusting that computers have enough battery these days.
It's not very clever, that, is it?
A power source.
This is not apparent. Oh, your battery looks like it might last for a long time.
Yeah.
I think
I think it will work. Oh, it will work. Let's hope.
Oh, you're dual screening, not mirroring. I wonder if you want to change that.
It's fine. I'll do something like
there
this.
we go. Right. Are you ready to begin?
Almost.
Almost. Good.
I just wanted to.
Good.
Well, that's a bit inconvenient.
No.
Okay.
Great. Welcome back, everybody, to the final session of MPLR 2025. And our session comprises 2 full-length talks and 3 short talks. Our first speaker is Dimi Rakoda, talking about existentializing your generics. Thank you very much.
Thank you very much. So, hello everyone, my name is Dimi Rakoda. I'm a professor at HSSO, and this is joint work with former colleagues from APFL, Pat Bovel and Hamza Randall. So I'll be talking about generics. So to talk about generics, we need to have some generics. I will be using a lot of Scala to talk a little about this research, but this applies to your local friendly generic programming language. But here, let's look at this program. We have a trait, a shape here. You can think of it as an abstract class, if you will. And this has one requirement. I want to have an area method. And I have a function. Here I'm using Boolean polymorphism. So total area is a generic function, and I want S that is a subtype of the shape. And then I want to just take a collection of shapes and sum these areas. Right? It's very simple stuff. I'm sure everyone here understands what's going on. And we can write this kind of program in Java, in Python, in you name it. Okay. So how can we apply this program? Well, we can do that. For instance, I'm creating a circle, and the circle is a shape. I'm implementing the area method, and then I'm applying the generic function. Now, when I apply a generic function, when I want to compile the generic function, there are 2 traditional approaches. There is the monomorphization approach. That is what your C++ compiler would do. The monomorphization approach consists of essentially rewriting your generic function by substituting the types with which it has been instantiated. So for instance, here, that would be the same as rewriting total area for an array sequence where I've fixed the circle type as being the shapes for which I want to compute areas. The other approach is erasure, and this is what is typically happening on the JVM. So in Scala, in Java, when we are compiling to a sort of type arrays representation of the objects,
And now there is only one universal representation of your generic function, if you will, that is compiled and then executed by your machine. And it's software engineering. There are pros and cons to both approaches. When we go through monomorphization, the cool part is that we get no runtime cost. It's as though you had written the function directly yourself with no generics involved. It's also compatible with inline representation, so efficient representation of data structure, but I will come back to this point later. On the other hand, we get more code, right? Because every time I want to use my total area function with a different kind of shape, I need to rewrite the same function again and again and again. These are very, very similar piece of code, but it's a lot of code nonetheless. And also, I cannot have separate compilation. Every time I want to instantiate my total area function with a new type, I need to recompile it. I need to go all the way through optimizations and so on and so forth. And this is one of the big reasons why C++, for instance, is slow to compile. Now, if we go with erasure, we don't get these drawbacks. We have smaller code size because one implementation, one compilation of the total area function is enough for all the possible shapes that you could imagine. I do have separate compilation. I can put that in a jar, and then I can reuse that jar for any other new subclass of the shape trait. But at the same time, I get the reverse from the monomorphizations, right? So I get runtime costs due to boxing my representation, and it's incompatible with inline representations. So what about these representations I keep mentioning? Well, on the JVM and in many reference-oriented languages, so your typical object-oriented programming language, if I do something like that, so this is the definition of circle. So circle is composed of an origin, which is a two-dimensional vector, and a radius, which is a double. And if I create an instance here of the circle, this is roughly what I get in memory. I get a first object that represents the circle here. It has a bunch of stuff, a mark, a pointer, a class pointer, and then finally I have some payload. And the origin is just a pointer to some other object that also has its own mark pointer, class pointer, and so on and so forth. So it's a lot of memory for just the actual bytes that I'm interested into. Well, actually double is 8 bytes, sorry for that. Let's pretend that I wrote float. So I really need only 12 bytes to represent my circle, but I have much more memory that is used here. And also I have all these indirections going on, right? I need to follow the pointers and so on and so forth. So in some applications, this is perfectly fine. In some other applications, maybe that are a bit more resource hungry, this is unacceptable, right? If you talk to designers of graphics engine, they will frown upon these kind of representations. So if we were to write that in C++, instead, we would get what I call an inline representation. So C++ is very proud of their zero-cost abstractions, which essentially is here represented by the fact that I can create a vector, a circle, put the vector in the circle, and I can do all sorts of wrapping. At the end of the day, I get my 12 bytes, or really 3 times 8 because it's a double. What's also nice about this inline representation is if I want to put my circle in an array of circles, then I need exactly that, right? It composes very well. As I said, you can wrap this into other objects or into arrays, and here I have only exactly the same sequence of bytes that I can put in contiguous memory. It will be very efficient if I want to do repeated access, for instance, in a loop, in a hot loop. So if I wanted to implement my total area function in C++, here is how I could do it. You could complain that I didn't use a smart type, but it's for the sake of making this representation simple. I have a pointer to an array of shape, which has this packed representation that I showed before, and I have a length, and then I can just run this loop. And well, if I go all the way down to the assembly code, then I get a bunch of stuff, but more importantly, I get that. This addition here is just computing the next index, and I just have to move a pointer into a large buffer. If I were to do that, were to look at what the Java code is doing, there will be a lot of indirections going on. So this is where the optimization penalty comes from the box representation. Okay, so this is about the representations. So now let's go back to the question of how we implement our generic function, and let's try to find another way to represent generics, one that is not based on subtyping. We will use type classes. It might be a bit scary. I'm sure the ICFP people here are very, very well aware of what type classes are, but for the other people, I will just do a very quick crash course. For ICFP people, it's the right time to check your emails. Okay, so we started with this code, right? We had the trait shape, and we used a bounded polymorphism to write our generic function. So the first thing we'll do is we will create another class here, well, a trait, and this is now parametric over this type self. Self will represent the type that are shapes. And the next thing I will do is that I will create the circle. The circle does no longer extend shape. Instead, I have this side function here that is creating what I call a shape witness. A shape witness is just an instance of shape for the circle. So basically, I'm just extracting the implementation of the area method in a different object, right? And the type system is not aware of this switcheroo. It's just me saying that the definition of the area method is somewhere else. Now, how can I apply this in a generic function? What I can create, it's a bit simpler function than the total area one, measure, that is just applying here the area of a shape. So it's a generic function, but it's no longer using bounded polymorphism. Instead, I'm just taking one generic parameter, and I'm taking two arguments. So one is the shape, and one is this additional side object that contains the method I'm interested in. And then I can just apply this method on the shape that I want. So this is nice and all. It re-implements the functionality that I had before, but this is a bit syntactically heavy, so let's see if I can use some sugars to make life look nicer. So the first thing I can do is to use context parameter or implicits. So instead of just a regular function, I will create a given function. This is essentially just introducing the instance in the implicit context. What it allows is that now the compiler can resolve on its own this shape witness parameter. I no longer have to write it down, so I can just remove it from my program, and it just disappears. And the next thing I can do is I can use this extension method in Scala, which is essentially another syntactic sugar trick that I can use to get back my nice dot syntax, dot-looking syntax. And the last syntactic trick I will use from the Scala tool belt is what we call a context bound, and now it looks almost exactly like the code that we would have written with bounded polymorphism. So I've done a lot of Scala tricks here, but I've done that to show you that type classes are really just reusing a concept that we already know. We just put the data on the side, and then we add parameters. And the syntactic tricks here, they can also be implemented in other programming languages, so it's not a Scala-specific thing. For instance, if I were to write the same program in Swift, it would look almost identical, right? So type classes is a sort of a general approach that we can use to implement generics. Now for the ICF people, I hope you finished reading your emails, because this is the part where we bring things back. Okay, so with type classes, another interesting thing is that we can show that the two techniques, the traditional techniques to compilation that I showed before, can be represented using the type classes. So for instance, I can show static dispatch. Static dispatch is what C++ is doing. In C++, when we do the monomorphization, because we have substituted everything, the compiler knows everything. It knows the information of where we want to dispatch a particular method. So the RM method can be resolved statically at compile time. We don't need to go through a virtual table, no dynamic dispatch, and so on and so forth. And with the type class approach, we can do the same, because essentially what we can do is partial application of the measure function, and the argument that was passed that represented the witness that circles are shaped can be passed to the function directly. So we can do, with just partial application of the function, we can do static dispatch. So that gets us close to monomorphization. We can also show dynamic dispatch. So to get dynamic dispatch, what we can do is in Swift we can write this any shape. So shape is a type class, and writing any in front of it creates what Swift call an existential container. An existential container is basically a pair that contains a witness that some type conforms to a type class, so an instance of that type class, and a value of the type being witnessed. So here, the any shape can contain a circle and a witness that circles are shapes. And now when I call s.area, I will do essentially dynamic dispatch, right? Because the witness can be understood as a sort of virtual table. It's just that I've expressed my virtual table directly within the programming language itself. So it's no longer a built-in thing that comes with object orientation. It's something that I constructed. And this gives me a lot of flexibility to play with these representations. Right, so this is an interesting here application of type classes. And if you're interested in existential containers, we presented a paper last year at MPLR explaining how this works in more details. I invite you to read it or ask questions at the end. Okay, so now we have monarchization and we have dynamic dispatch or erasure through type classes, but can we do better than the existing approaches? And this is where existentialization comes. So existentialization is the process of trying to get kind of the both sides at once. We want to have the inline representations. We want to support separate compilation, but we need to have both of those things, right? So that was not possible with the erasure because we needed the box representation, and that was not possible with monomorphization because we couldn't get separate compilation. So what else can we do? Well, let's say that our shape type class that we had before, it had this generic parameter, right? So it was a shape of self, but now we create any shape. So this can be thought as a sort of erasure, right? I'm erasing the generic parameter of the shape. And then I have now my function area, which takes an any, right? This is also the erasure of the self parameter that we had before. But I know that my area returns a double. This doesn't change. The measure function that we had before, it also had a generic parameter that I need to erase. It gets replaced by any. And now I have this additional parameter, the w, which is the any shape. So it's the type class version approach that I had before, except that the context parameter, that was the type class instance, is now taking as an instance of this any shape trait that I have. And how do I implement now the body of the function? I just use my witness and I call the area method on it. It's basically exactly the code that we've seen before. Now what's interesting about this representation is that this is the only representation that you need to apply any instances of the measure function. I can use this measure function for the circles, for the rectangles, and for the triangles. It will not change the compilation of this specific method. So I have one on the separate compilation side. This one compilation result is enough for all the possible applications of shapes. Okay, so let's move to a more complicated example now to see if we solve our second goal. Our second goal is was to support the inline representations. So this was our original motivation. We want this total area function that takes an arbitrary sequence. I don't know what kind of sequence I will use. It can be an array, can be a list, can be a tree, anything you like, and a shape that was subtype. So we know already how to replace the bound here on shape. We can use a type class instead of this subtyping relationship. But how can we deal with the sequence, right? Well, we create another type class, right? We can create a type class that represents sequences. So this type class here is a bit more complicated. It has two generic parameters, one for the thing that is a sequence, and one for the element that are contained in the sequence. And here, there would be many other things in a sequence type class, but for the sake of this example, I just use the fold left function. So let's assume our sequences just have this one fold left function, and fold left has this signature. It has one more generic parameter. This is the type of the accumulator, and then it's, I didn't write any implementation, but I'm sure everyone here understands how to implement fold left. Okay, and then this object sequence type of is some Scala salad that you don't need really to care about if you don't know Scala. It's just some syntactic sugar that I wanted to be able to write a nice definition of my total area function. So now total area function takes S, that is a shape. It uses a context bound. It's not a upper bound on shape. So I want an additional parameter witnessing the fact that S is a shape, and I do the same thing for T, so that means I want another parameter witnessing the fact that T is a sequence of specifically S. And then I can write fold left. So this is what I write in the user level, and this is as safe as we had before, but now just expressed with type classes. Why I wanted to use type classes here, because now I can run the process of doing existentialization on this particular piece of code. So what happens? First, the sequence type class definition becomes existentialized, so I just erase its parameter, so it becomes any sequence, and all the occurrences of generic type parameters become just any. So the fold left is a function that takes any. This is the sequence itself. The accumulator is also an any, and the function combining the elements with accumulator is an any to any pair of any to any. Great. And now the total area is also existentialized, so we get x's. This is the any, so we want to the sequence on which we are that we have the sequence of shapes that we want to compute the areas. And then we get two additional parameters which correspond to the context bound that we had before. So the fact that S is an any sequence, and the fact that T is an any sequence, and the fact that S is a shape. It returns a double as before, and what is the implementation? Well, it's basically doing dynamic dispatch, right? I just need to add this as instance of because I wrote that myself in Scala, but you can imagine that the compiler knows that these casts are fine, right? So here we are just recovering the information that the accumulator was doing additions on doubles. This we knew from the original definition. So what's interesting here is that now, again, this one compilation, this one version of the compile function is enough to be applied to any sequence I want. Why? Because when I want to pass an array, I can definitely pass an array to an any, right? Any will accept anything. And how are we supposed to decode the array to compute the next element? Well, we just ask the any sequence instance that tells me how to get to the next element of an array. What happens if I use a linked list or a tree? Well, same thing happens. I can pass my representations unchanged, and then I can use the instance of any sequence here that is witnessing how to compute the next element. And well, there is that. That's the existentialization. So there is much more in the paper, and that requires a bit more context to be set up. Was difficult to fit in just a single presentation, but as a teaser maybe of things that I didn't talk here, in the paper we explain how to do partial existentialization, because the nice thing is that this replacement of generic parameters for any, you can choose how much you want, how deep you want to run it. And that lets you do to combine monomorphization with erasure. So basically, you get a cursor that tells you how much you want to monomorphize your function. And so the trade-off between fast code, because there is some runtime here, runtime cost due to the casting, for instance, but you can decide how much of this runtime cost you want to pay for in exchange for having more code. I didn't talk also about the way to allocate instances of existentialized type. So in these examples that we had, it was kind of convenient that all of the instances that we wanted to use were already in memory somewhere. But if you want to create new instances of your existential parameters, in the monomorphized world, it's very simple. In C++, for instance, you know exactly what is the size of a circle, but if it's existentialized, you might not know. And well, this is additional information that you need to carry through with your witnesses. And this is explained in the paper. Another thing that is also interesting with existentialization is that you get type reflection for free, because basically these witnesses, they explain what your type is, and so you can just consult the witnesses to ask various questions about the size of your type, the layout of your type, and this is how programming language like Swift, for instance, implement their reflection. And finally, in the paper, we have a bunch of benchmarks showing that the overhead of existentialization is reasonable in languages like C++ and Swift that normally use aggressive monomorphization. So basically, we are paying for the additional cost of doing dynamic dispatch, and these costs are relatively well known, and there was nothing very surprising here. What was a bit more interesting is that if you try to apply existentialization on object-oriented languages like Scala, you get exactly the same performance, because in fact you just implemented virtual dispatch manually, and Hotspot doesn't care. And Hotspot optimizes it the same way. And well, if you want to learn more about that, you can read the paper or come to see our poster on Thursday, where me and my colleagues will be there to answer your questions if you have any. Thank you very much.
I'm going to invite the next speaker to set up their slides while we take a question or two, please. Thank you. So we'll move on to our second talk now, and Christophe Pichler here is going to be telling us about GraalVM native image and how to make it small.
Thank you for the introduction. As said, my name is Christophe. I'm a PhD student at the Johannes Kepler University in Linz in Austria. And yeah, thanks for attending this talk. As you see, the title is not that fast and compact, so we will break it down a little bit and talk about ahead-of-time compiled Java code, or GraalVM native image, as already announced. So GraalVM is a polyglot virtual machine, can execute and interpret different languages. There is an ahead-of-time compiler there. There's also a just-in-time compiler there. And today we focus on Java code. So how does this work? It's a little bit more described in detail in the paper. In general, you have application code, and you also have the JDK, the library, the runtime, and your methods, your compilation units are laid out there. And GraalVM native image performs a reachability analysis, detects unreachable code. This code is then removed, and the rest of the code is then compiled into machine code. So far, so good. And this is also not my work yet, of course. And if we now take a look at Java, at this procedure, so we start with Java source code, we compile it to Java bytecode, and then it's further compiled down to machine code, and then we can actually do a size comparison. And so on this diagram, on the x-axis, you see the bytecode size of a compilation unit. On the y-axis, you see the machine code size. All dots on the line mean that the bytecode size and the machine code size are equal, and every dot is now a compilation unit of the capo benchmarks. And as you can see, on average, the machine code is larger. On average, is 3.1x, which means we produce very large binaries if we compile applications. So we might reduce the size of ahead-of-time compiled Java code. And since we saw that the intermediate representation is smaller than the machine code, we might just replace it. So what is happening? We have an application with certain compilation units, and we remove certain compilation units. Of course, to make the program still, or to keep the program valid, we have to add the corresponding code we removed, but we now add it as bytecode, which takes less space than before. So now, of course, we still cannot directly execute the bytecode, so we still need an interpreter, and more information on that later. We also need a JIT compiler to keep performance, but as said, more on that later. But still, if we're lucky, we get savings, and this is what we want to achieve. So small introduction, kind of behind the scenes. How is this working? We have our Java code as bytecode. We apply it to the ahead-of-time compiler. It also does some profiling, so it injects certain data. PGO stands for Profile Guided Optimization, for those who do not know this part. And then the ahead-of-time compiler generates a final executable. What is also created by our approach is a metadata file containing the bytecode of the application we want to compile. And we also extract a list of all compilation units. And for that, we can decide if we want to keep the compilation unit as ahead-of-time compiled code, or if we want to interpret the compilation unit instead and store the smaller version, so to say. And for this decision, which I will talk later on the next slide, we can also use the profiling data, of course. What is then still necessary, and our current approach, this happens at runtime, is to redirect the execution. So at the start of the execution, there's a small initialization phase, which runs over the interpreted compilation units and just forwards the method entry. So there's the global offset table, and that corresponding entry is modified such that if we call a method which is said to be interpreted, then the interpreter starts instead of the machine code which is not available anymore. So now let's look a little bit into these heuristics. How do we currently decide how to execute the compilation unit? So as you can imagine, if we have a very large compilation unit, it makes sense to interpret it in general, because then otherwise it would take a lot of space. On the other hand, of course, we only care a little bit about performance, or not only a little bit. We also have long-running application units. And since we already have the profiling data available from the GraalVM native image compiler, we can detect compilation units that are long-running. For example, they contain a loop. On the other hand, there are compilation units that are called many, many times. These are also detected by the profile. And if we just put those three numbers together, we get a rather simple but useful metric, which kind of estimates, so we get a number, and that number can tell us if it might be better to interpret it or if it's better to keep it ahead of time compiled. So as you can imagine, there is a trade-off between size and performance. And what we can do is we have our application with all these compilation units, and we can sort those compilation units by our metric number. Then I plotted this on a diagram here. So at the x-axis, you have the code savings, so how much were we able to reduce the code. And on the other hand, we have the execution time of the application. So when we start, of course, we don't have any code savings, and we get a certain execution time. Then, for example, we can decide to remove the compilation unit h, save some space, and then execute it. And then, for example, we see that h is not performance relevant if we interpret it. So rather lucky. It can also happen, however, that we remove the next compilation unit, and then we see that performance increases. So now we are at an unlucky state. We can proceed this analysis. Of course, we don't have to do this for every single compilation unit. You can also remove them bucket-wise. Then you get a diagram kind of looking like this. Of course, our goal is to be at the right bottom part, because there we achieve greater code savings while execution time is still low. Short side remark on that, not every code can be interpreted. One reason is, for example, you cannot interpret the interpreter. So this was one of the first things I discovered. Yeah, I just ran into a Stack Overflow, because if you want to interpret the interpreter, of course, this does not work out. And there are also some other code parts that have to be ahead of time compiled. Those are just known by a whitelist or by a block list, and then you're safe to go. So I'm also teaching basics of software development, and just took homework where the students had to implement a single linked list, and also tried our approach with this very simple application. And there we could get such a diagram. So now you see the resolution is way more higher than just 8 compilation units as on the previous slide. We can see that there are a lot of irrelevant compilation units. So when we interpret them, there is no real big change in performance. However, the linked list add method, it's just one compilation unit, but it doubles the execution time. And our simple metric was not able to detect that, kind of. And we also realized that we will never be safe if we just use heuristics. It can always happen that we are unlucky and just detect such a small method that really causes problems. So further to approach the full title, of course we don't want to sacrifice performance. And for that we take a look at the execution modes in general. So for our current approach, we combined ahead of time compilation and interpretation. So we are kind of moving along this axis. We started from ahead of time compilation and then went on further. And as you can see here, ahead of time compilation achieves a high peak performance. On the other hand, interpretation leads to small file sizes. However, we can actually complete this triangle and insert just-in-time compilation as well, and try to move inside the triangle. So instead of pick 2 out of those 3, we try to get the best of all 3 by applying just-in-time compilation and by saving the performance. However, before really implementing a JIT compiler, we simulated it first, just because of a research question. If we include it into the final product and then we realize this doesn't really work out, it's a lot of wasted time, and therefore it's a rather cheap cheap simulation. So what we do is, because we have to decide at runtime if we want to JIT compile a method, what we currently do is we just take the time between 2 subsequent calls of that compilation unit. If it's large enough, we continue. If this is below a certain threshold, we just JIT compiler method. And JIT compilation means, in this case, we just replace the bytecode again by the ahead of time compiled machine code. So this is no real JIT compiler, this is just a simulation, but you will see in the next slide that it's not as bad as it sounds in the first place. So on the left we have a diagram of the Capo-FOP benchmark, which does PDF layouting, and there it's the same approach as before. We remove compilation units and then just take a look how performance evolves. And if we now add our JIT compiler or our JIT simulation, we see that the performance is way better. Please mention that the axes here are different. So I note that the 130 line in the left diagram. What we can also see that the deviation gets a little bit stronger. But on the other hand, you see that with only JIT compiling 5% of the interpreted compilation units, we can actually achieve a way better peak performance. And this is also a reason why we saw that this is useful, because 5% are not that much. So just by removing very few methods or compilation units again and JIT compile it, we keep peak performance. And this is also, so we don't have concrete measurements for warm-up performance here, but since it's only 5%, we claim it to be not very large. Another aspect I would like to emphasize about our approach is that the savings need to compensate the additional code. What do I mean with that? So again, there's a diagram. The machine code size of the original application is the x-axis, and the code savings are on the y-axis. So code savings is the difference. You have the original machine code, then you remove some parts of the compilation units and add them as bytecode instead. And this is the difference, what I call code savings. Of course, to be able to still execute the program, you have to add the interpreter and the just-in-time compiler. These are constant 14 megabytes, and you see the pay offline here in this diagram, which means, for example, if we have an application of 100 megabyte, we see that we have to kind of save 15% of the code savings such that our approach pays off. Of course, for very small applications, the interpreter overhead and just-in-time compiler overhead is very high. And on the other hand, for larger applications, size reduction is achieved really fast. How does this look like for concrete benchmarks? So here you can see the capo suite. Again, the FOB benchmark is achieves one of the best results because it has very large file size, 180 megabytes if you compile it to machine code. And as you can see, we could achieve 44% of code size reduction. If we add the interpreter and the JIT compiler again, we have a reduction of 37%, which is quite nice. On the other hand, the LO index benchmark, for example, we could save 10% there, but since it's a rather small benchmark with the overhead, we produce an even larger file. So for smaller applications, our approach is currently not really, or does not really make sense to use. However, if you think about the cloud environment, for example, also the Spring Pet Clinic benchmark is added here. We could achieve 20% of the code savings. So if you use less memory to save the file, it's also usually lower costs. Some comments on related work, because I'm not the first person who tries to mix execution modes. Also for Java code, the Android runtime does something similar, but they're doing actually from the other side. So they start with interpretation and JIT compilation in the first runs, and then in subsequent runs, they also detect code which should be ahead of time compiled. It's not that they don't focus on file size at all, but I said they approach the direction from another part, because we are starting directly from the ahead of time compiled code. There are also different research groups. I summed it up with JIT caching that try something similar as well. Some of you have heard maybe about Project Leiden. So they are also trying to include ahead of time compilation into Java execution. This is still in development, not in the very early stages, but as said, still in development. And maybe some of you has also thought about native extensions where different execution modes are mixed. The things for native extension is that the execution mode is selected manually by the programmer. So for example, if you think about Python or Python and C, where those languages are combined, as a programmer, you decide by the programming language how it is executed. So C code is ahead of time compiled, while Python, on the other hand, is interpreted and just-in-time compiled. And last year at VML, we showed an automatic approach where we could actually also improve the results. So we could take an existing Python or Python application and prove that our manual detection of the execution mode actually works better than programmers letting decide the execution mode themselves. So what I would also like to mention is that my approach is not not finished yet. One of the most interesting things concerning research, in my opinion, is how important is profiling data. So in the current approach, it's easy to know how large the compilation units are because this is known in compile time. But currently, as said, we rely on profiling data. And it would be nice to get rid of those profiling data, the question is, how important is it? How much worse do we get? And can we get to a reasonable approach without this profiling data? So this is my most important interest currently to improve Zoom. And with that, I clicked on the wrong thing and might get to the correct slide again, but I'm almost at the end. So what did we see? We see that Java files can get really, really large. However, we can shrink file sizes by just removing ahead of time compiled code. And at the intermediate representation again, we have some decision progress and some heuristics, which currently work quite well. However, the question is, can we, also concerning JIT compilation, we achieve quite nice results for larger files. The question, as said, is how do we perform with our profiling data? And with that, the presentation is actually a little bit faster than expected. But now I would hand over to the question and answer part. Thank you.
Thanks, Christoph. Let's take some questions, please.
File sizes are an important criteria here too. So one question. You mentioned, I mean, the premise is that, AOT compiled code is larger than bytecode, and hence shrinking file size is important. So how does, in general, for Java programs, real Java programs, the size of the JIT compiled code compare with AOT? And if it is less, how does it differ from reusing JIT cached code? Like, I mean, you just mentioned it briefly, but I would like to hear more on it.
As said, we're currently only simulating a JIT compiler, so it's only a proof of concept that it makes sense to include it. But we actually have not included a JIT compiler directly. Okay. So currently we are just switching back to the larger code, which is of course not nice for file size. If we keep the JIT rate, so to say, low, because it's 5% for all of the benchmarks, or below 5% actually, then we also see that the effect on the file size is not that high because it's not a lot of methods that are JIT compiled.
Okay. But in general, would you, I mean, can we assume that JITed code size would be lesser than AOT compiled code? I mean, you have PGO, but fewer optimizations.
It's a good question, depending on the speculation part. So if speculation, for example, works nice, then I can imagine that the size gets smaller. In the worst case, it gets as large as the AOT compiled code. But I cannot give a concrete answer to that, unfortunately, no.
Small question. Let me clear the motivation. So you want to reduce the size of the ahead of time compiled code. So why do you want to reduce the size? So the storage price is relatively cheap. So why do you want to reduce the size of the compiled type?
If you compare it to other file sizes or to other execution modes, the size is still larger. For example, also on your phone, you could fit more apps if the space is already full. If the app would take less space, and also for cloud environments, it's.
I see. So not for the server side, but for the devices, something like that.
Sorry.
So this research is for the such small devices, not for the server side applications or something like that.
So our application works better for the for larger applications. Our approach, but also for server size, of course, you pay less if you need less space.
Thank you. So I'm also curious about the motivation. So for the leftmost picture, so it's just-in-time compiler is included in the native code, native image. So I think, but just-in-time compiler just generates more code than you expected. So how do you think about the compensation about the JIT just-in-time compiler generated code?
And currently we only use the JIT. So in this calculation, we only included the JIT for the sizes. For a real application, of course, as said, the cheat rate is rather low. So we really use the just-in-time compiler only to compensate the errors of our heuristics. So it's not the goal to just-in-time compile all of the compilation units, but just if our heuristic does not thinks that we should interpret a compilation unit which is really performance relevant, only then we use the JIT compiler to wipe this error kind of out. By that, the influence is not that high on the total memory.
Okay, thanks so much.
A last question, please.
I wondered, are you storing the compiled code in a compressed form, or is it just stored plain in the executable?
Currently, it's just the executable. There's another PhD student in Belgrade, I think, who tries to compress certain code. So they have the drawback that they have to uncompress code again if they need it. Of course, on the other hand, if we do a wrong decision, then we have a bad performance. If they do a wrong decision, they have the advantage that they only have to unpack it once and then have the full performance again. So we haven't considered compressing it yet.
Thank you.
Let's thank the speaker again. Thank you.
Thanks, Christoph. James is going to plug in here. Good. So we're now on to a set of 3 shorter talks. These are 15-minute talks, and we should be strict with our timekeeping. James Noble is going to talk to us about abstract syntax trees and why you should look for them everywhere.
Yes, well, actually, no, it's not about why you should look for them everywhere, but I'm pleased to be giving a short talk. Unfortunately, I'll have to dash next door to something straight afterwards. Yeah, flexible ASTs are fast and easy for flexible embedded interpreters. In the beginning, as we all know, there was Lisp. And if you're building a Lisp, you have to build a Lisp reader. And, you know, I encourage you all to forget about everything that Racket and Rhombus has taught us and about reader macros and macros and syntactically pure macros and macros in a syntax that almost look as if it could have been designed by, I don't know, Niklaus Wirth in 1970. Because really what you just have to hard code the bloody Lisp reader, and even if you look at what the Racket guys or the Rhombus guys are doing, they use that to bootstrap the system, and then they bootstrap on top of it, and they bootstrap on top of it, and eventually get their wonderful pile of macros. Smalltalk, well, in the beginning from Smalltalk, I do like Smalltalk. This picture is kind of irrelevant, but I thought it was funny. Because it talks about parser franchises. The Smalltalk parser is built into Smalltalk. In the image, which is basically a pile of steaming bytecodes that was originally written, I believe, in 1972, and then exported out of Smalltalk 72 and into Smalltalk 76, and then exported out of Smalltalk 76 into Smalltalk 78, which uses the same bytecode format as Smalltalk 80, which uses the same bytecode format that we run today. And you can actually go to a web page, I'm not going to, and load in an image into JavaScript interpreter of Smalltalk 78, I think it is, or some, in fact, no, Smalltalk 76, and you can run it there. And you just load up the bytecode and everything works. Right, for the young people in the room, which is almost everybody, there's Jason, right? If you want to load some random shit in, you just call Jason. So the problem we are facing, or have been facing, is we're developing this new language called Grace, which we would kind of like to bootstrap it. Well, when I say we, you know, because there's only 2 of us and we're kind of daft. Grace lets you write code like this, which means it does need a parser. In some ways, part of the design philosophy of Grace is that it's not that we hate macros, it's that we think that another level of indirection on the syntax just makes everything worse for almost everybody else. So, I'm sorry, that's a gentleman is giggling in the background. Excellent. This talk was actually a work in progress research talk, which means I have a feeling the program committee thought the entire paper was a joke. I was going to say, compared with the previous talks, there's the program committee, where the previous talks, which were about building something for a really huge, big commercial project, like, you know, I mean, Graal just starts for hotspot and then adds in piles and piles and piles and shit. This is kind of the opposite. Because basically there's kind of none of us actually working on this project, And it's absolutely clear that having an awful lot of money, whether you're from a venture capital firm or from Sun or IBM, really helps your programming language projects. But, you know, to quote Ernst Rutherford, we don't have the money, so we have to think harder. We'd like to implement this. It's a teaching, or we called it a teaching language to justify working on it, because if we said, look, we'd just like to do a new minimal uninteresting object-oriented language, everyone would have thought we were crazy right out from the start. So what can we do? We're interested in this language. We're interested in running it on various platforms, which basically means hosting it in other languages. Well, after, I don't know, too long sleeping or too long drinking, we kind of realized this. Algol. And there's that snide comment on the side that says the one true algol is C. What I mean here is that, in fact, if you are extremely careful about the way you are choosing to, I guess, export or pickle or whatever word you want to use your ASTs. And in fact, you can't actually do it in the standard algol syntax. That's why I say the one true algol is C. You get something like this, which is obviously horrible. But the point of this is that it is syntactically correct without even running it through TR in a large fraction of all the programming languages you are ever likely to want to host this damn thing in. Maybe you've got to write a little bit of it. You do have to write some support code, because those are the AST nodes, so you will have to do something to actually build the AST nodes. But if you're writing an interpreter, you've got to do that anyway. And if you're clever with a little bit of tweaking, you can then start loading in files like this, which means that we could have an awful lot of other stuff, including the Grace parser, including the Grace standard library, all these kind of things. Particularly the parser, I guess, because once you bootstrap the parser, you can bootstrap everything else. And so this is syntactically correct in a whole lot of languages, and if you're willing to do TR, you can actually get to things like Pascal, which traditionally has different quote marks, and Smalltalk probably has different quote marks, and whatever. You can get to those kind of things with really very little effort. Prolog you can probably do. I don't think we have done. That's really the point of the talk, okay? And I figure the paper got in because one of the program committee members, who hopefully isn't in the room, said something like, this is a completely daft idea, blah, 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 but maybe I'll use it in my next project. So I'm glad this got in because, you know, I often say, well, look, the best ideas are kind of obvious in retrospect. And I hope this idea is obvious in retrospect, and it'd be nice to have this paper out in the world so that if somebody else has a similar problem you want to, maybe this is student work. Maybe, for example, you're giving your student the exercise to say, well, let's write a toy little programming language. This would say, you know, you can give people these ASTs, and, well, either they can pass them in themselves, or what's even better is, when I say it's syntax, it's valid syntax across all these languages, I mean, it's valid syntax across all these languages. So you can just write the library code and you can link it against that. You don't even have to have a reader, because you can just link it, these ASTs, directly into your source code in pretty much any language that you can think of. So everyone knows my background is object-oriented, so anyway, Michael is a more generous chap. But here's the Haskell stuff, basically. This isn't all the Haskell code you need. I can show that briefly if I don't run out of time, but that's basically it. There is a program, line 16 to 19. At the very bottom, you actually have to go off and tell the Haskell code to run it. These are the, well, I guess lines, the top lines here, cons and while and nil. Object, there's the definition of the object constructor. So we're actually defining a Haskell function that takes a tuple, which is a body, which is a recursive call on these things, and the annotations. And what this is doing is basically a bit of syntactic sugar using the C/algol/whatever calling convention, or what OCaml does, where you actually pass in a tuple, and then it's desugaring it into a something which is Haskell. We know it's Haskell because it's capitalized, and it doesn't have those parentheses, and it doesn't have any commas. That lets us read this stuff into Haskell, and then, you know, down the bottom, I guess there is an interpreter, which I think that's it, yeah, an interpreter from a context to an I/O. This is actually running something that is the interpretation of a number node. So you write the, you write the interpreter like this, and then you can supply these ASTs and people can run it. So, if were I to be giving an assignment to say write a code, write a program, a simple interpreter for something, I could give people all these ASTs and they can link it against their Haskell code or whatever else they want to link against, Java, JavaScript. But I'm not sure about, Camel does weird things with quotes. But anyway, a whole bunch of stuff. And they'll be able to run these test cases. So you could say, write an interpreter in whichever language you like, we don't care. Here are the test cases. You don't have to write a parser, but you will be able to link them against pretty much whatever language you pick. And if you can't link it against the language you pick, then don't pick that language. Do I mean any language? Well, it gets stupid, right? Simon Peyton-Jones isn't in the room. Alan Blackwell isn't in the room. They put Lambda and functions into Excel. Why? I don't know, because why would you want to? I mean, it's got its own extraction mechanisms and it's a spreadsheet, and it's not entirely convincing that having function definitions really helps you do anything with Excel. And I'm not even sure what Michael is actually doing here, but right up the top you can see, wow, okay, I've expanded it halfway down here. There is the same syntax, which is the syntax for the Grace program I showed you. And yeah, it's being loaded into Excel, and somehow it's spitting it out into various bits and pieces. I guess it's showing you the tree structure at least. Software visualization, sorry, that was my PhD. Right, represent. Okay, completely daft. Of course, when I mention all these languages that have syntax, fits into Grace syntax as well. So, you can do this kind of thing where GRASP pulls in the definitions for the nodes of the AST, for the Grace AST, and then, we can write a program there, or we can pull it in from somewhere else, and we can run it, and we run it. I think I was supposed to finish at 5:05, was I? There'll be time for questions. There we go. This is a visualization done by cutting, and I did not use AI in any way in manufacturing this talk, cutting and pasting the icons for all of your favorite programming languages. And if you would rather like to have your language on the slide, we'll accept money, because I'm no longer at a university and I'm kind of looking for a job, and yeah, I might be forced to go and work for a bank or something, but with the tax department in Wellington. But until then, doing this sort of stuff. So yeah, we've got, what is it? All of those ones we actually have ASTs running for, and then, so we have the AST readers, and on the right-hand side we've got the languages where we've actually managed to, Michael has written the few pages you need for a Grace interpreter. So that's basically it. These kind of fast ASTs can be embeddable, fast and easy. And I've got a few minutes left for questions, or if you really don't believe anything I've said, is that font big enough? Oh, sorry, it's done that thing, hasn't it? Now, I have to remember, oh dear, I pressed the wrong button. I don't know, there it is. I was going to say, I don't know which side of the screen this is, and now it's impossible to drive the mouse because it's backwards and I can't actually see what is going on that screen, but yeah, hello world. If you say, whoops, if I say produce the AST, well, I've already done that. There it is. If you don't believe me, whoops. Produce the AST, there it is. Hello MPLR, there's the AST. If you execute it, if I can remember how to do that, there we go, it's actually run it and spat the thing out on the far right-hand side. And actually, I lie. In fact, this is directly connected to the previous talk, because the previous talk was precisely about things like ahead-of-time compilation that you can then run. So if you want to do an ahead-of-time compilation of this, you don't want to run a Grace interpreter, you'd actually run a Grace interpreter that's kind of wrapped up in standalone Java, so we're doing nested interpreters. This thing should generate, I'm told, there it is, a great big Java. And what's the important thing? The important thing is that, okay, there we go. There's a whole lot of those definitions. That's the definitions of the AST. That looks like a visitor to actually run the thing. It's horrible, isn't it? Right, and then right down the bottom, I think, there's all the definitions. It's one file, okay, bang. Oh no, where is it? Can't find it. Because, anyway, I think we're not right down at the very bottom. At the very bottom, what the hell is it doing? There it is, okay? There is that AST. And the important thing is, you know, well, I mean, it seems pretty obvious one could do this in JavaScript. But just to be clear, well, that looks very much like the thing. We're at the bottom. So there was a const program, I believe. There's the same program, exactly the same AST. And when we say directly incorporated into your source code, we mean directly incorporated into your source code, which is what we've done there. And the fun bit, of course, is it will think a bit, presumably. Is it still thinking? Probably crashed. I mean, this is written in some combination of Grace and JavaScript.
We should give you a round.
Thank you. Well, I then will dash to the next. Damn, Haskell. Was it a joke? No, no. But you know, you can just cut and paste. You can just cut and paste the thing.
Yeah, very nice. Good.
Was it a joke? I don't know. Well, thank you once again, and I'm afraid I have to dash next.
Stone.
no, you're coming to do the next talk, aren't you? Okay, good. That's fine. I'll ask you a question then. Did you think about whether you could use standardized kind of data formats and then reuse existing tools for visualizations? I'm thinking about things like gprof or kind of flame graph profiles or something like that. Or did you have to really do customized stuff for your workloads?
Because we have already one way of indirection when we create the bytecodes, then that would be the problem, that we have another way of indirection if we are trying another layout for the standardized tool. So displays. Display.
Well, thanks. It looks like a nice tool. We'll give you another round of applause while I juggle my microphone. Thanks, Michal. And this is the final talk of the day. It's another demo. How exciting. It's also from Manchester. And Athanasios is going to give us today's talk. And again, this is about heterogeneous programs in Java. And again, it's using Tornado, I guess. And we'll be interested to hear what you've got to say in your demo here. Thank you very much.
Thank you very much. It's a nice opportunity to be here to present our work. So I'm Thanos, this is my short name. Athanasios is the full name. I'm also a research fellow as Michalis in the University of Manchester, and we're working on the same team, the Tornado VM team. So today I have the pleasure to present you a second tool that we have created. It is complementary to the previous one that Michalis shared. And the idea is that we want to share it from the perspective of the programmers to enable it, to make it easier for programmers to use Tornado VM and to access from Java the GPUs. So currently the pain points for Java developers is that they are used to IntelliJ and Eclipse, and these are fantastic tools for development of Java applications. They have integrated debuggers, profilers. You can create flame graphs. You can analyze the performance of your application and optimize it, and this is fantastic. But when we're talking about GPUs for Java developers, this is quite tricky. And the idea is this is because of two reasons. First, there's no clear indication for the syntactic issues that you may face. So, for example, in Tornado VM, we have some features that are not supported from the full Java syntax. For example, we have some unsupported data types, some POJOs that they are not detected at JIT compile time, so these are not supported. And yes, we have detailed them in the documentation, all of these. Also, recursive execution is not valid because in programming models like OpenCL and CUDA, this is not valid. And we have also the throne of exceptions, which is not supported from CUDA and OpenCL. So these are kind of, features that are not supported from Tornado VM. But who is reading the documentation? So we need the tool. And the second part is that in order to find out this kind of behavior, right now, Tornado VM developers, they had to build the programs and try them and get the error and then build again. A second optimization, no, it doesn't work. So this is the trial and error debugging process, which slows the productivity. So what is the problem? Well, errors appear late, too late, after runtime, and it is difficult to trace them. So our research question was, can we educate Java programmers to use GPUs? Can we make it easier for them to access GPUs, to understand the way that Tornado VM works? And that was the reason that we introduced Tornado Insight. Tornado Insight, it started as a master project by Thais, who is a co-author in the paper, and has been extended with the contributions of many people. So it is an open source plugin for Tornado VM programmers. First of all, we thought that IntelliJ is it's used by the majority of developers, so it is a cool tool to integrate and create a plugin for IntelliJ. It is currently available in the marketplace of JetBrains, so someone who has IntelliJ installed, they can download the plugin, install it, and use it. It can give instant feedback in the console of the IDE, so you don't need to change console. It is there in IntelliJ where you can see the actual output. It combines static and dynamic analysis, And it is open source. So it is available in GitHub. We have several contributors to the tool, and we have done 10 software releases, including the latest one that appears after the camera-ready submission, which is the 1.3.0. Okay, let's move a little bit into the architecture of the plugin. So this is a diagram, a block diagram of the architecture. It has 4 main components. We have with the blue component the static inspection, where we have integrated 6 types of inspectors. In a sense, these inspectors, they correspond to the unsupported features that I mentioned earlier in the presentation. So we have the data type inspector, the exceptions inspector, recursive execution for functions inspectors. And what these are doing is that at the coding time, at real time, they can inspect the classes, the Java classes, and understand if there is something that is supported or if it is not supported. Then we have the second box, which is the communication module, where we have implemented some listeners. In a sense, the listeners, they are observing at runtime this kind of behavior, and they can give some feedback into the panel of the plugin. I will show you the demo in a bit. And we have also the UI module, where we actually have the panels, the windows, how they will work and what information will be shown in the windows. We have a settings panel, so users can configure the Tornado VM directory where Tornado VM has been installed. They can configure an indicative array size that will be used by the tool to perform dynamic inspection. And yeah, all this. And we have also the console in the UI module, which is the actual outcome that comes from the dynamic inspection. And finally, we have also the green box, where we have the dynamic inspection. This is the part that will take the actual method, the Java method that the user has defined, and it will perform the dynamic execution. So it will trigger the JIT compiler of Tornado VM to report if there is any problem during compilation. And the process here in this architecture of the plugin is that developer is writing the code. He can run at real time, see any static analysis, any static syntax issues which are defined as not supported. And then he can click or she can click dynamic analysis to perform the dynamic inspection, and the feedback will come on the IDE. Okay, great. I think I have time for the demo. Excellent. So I have opened. Okay, 1 second. Perfect. Yes. Now you can see the IDE. Okay, excellent. So if we go to the settings of the IDE, we can go to the plugins, and we can see here the installed plugins. So here I have installed Tornado Inside, which is the latest version. And yeah, this is how you can actually install it from the JetBrains marketplace. Then once you have installed it, you will see here this icon. This corresponds to the Tornado Inside site. There we have part of the UI. Here we detect the actual detected tasks which are valid and are supported by the tool and the listener. And we have also a second part, which is the console that I will show you in a bit. But first, let's try to add the settings. So as you see here, we have the Tornado root directory, where we specify where we have cloned and built Tornado VM. Then we can define an SDK. So in this case, I will use the Graal VM Community Edition. Then Michalis kind of spoiled it. We have already integrated Tornado Visualizer, so users can enable or disable the tool and launch it from inside the plugin. And then they have to add to declare a size for the maximum array size. So this is in a sense the number of parallel threads that they want to launch on the GPUs. In this case, we will run matrix multiplication, for example, and we are going to use the 512 array size. And if they are using the Tensor API of Tornado VM, they can also declare the size of the dimensions for the shape. And we have also some options for debugging, which is useful for the Tornado VM developers, the Tornado Inside actually developers. So if we click apply and OK, we see here we have a matrix multiplication implementation. And we see that we have one method declared here for matrix multiplication. We're using the loop parallel API, so we have two annotations, that parallel annotations, which indicate the Tornado VM JIT compiler to implement the parallel implementation. I'm not gonna go through the full class because we don't have much time, but in a sense, if we refresh here, we see that this task has been identified. We can see that here we don't have any red exclamation mark, which means that the syntax is okay, static analysis has been validated. And now we can run the dynamic inspection. So once we have run dynamic inspection, we get this kind of message that has been completed. And here in this console, Tornado Inside console, we can see the parallel implementation, so the generated OpenCL kernel that has passed all the phases in the Tornado VM JIT compiler graph, and it has been generated. So this indicates that the developer is ready to launch the application and actually run it. So if I click this one, I can actually run the application on my MacBook. It's an M4 MacBook. And as we see here, it has been run and the verification is true. So we have compared the results from the GPU with the results that are coming from the Java sequential execution. Okay, excellent. So I have shown you a successful demo, but let's go to the breaking stuff. So we have here an example of a class where we declare an array list addition method. And if we see here, we pass as input array lists. But array lists, they are data structures, objects that are growing at runtime. So that means that this kind of behavior is not supported on GPUs because we cannot change the sizes at runtime. We need to recompile and we need to trigger this kind of behavior. So in this case, they are identified as red, as we see here, which indicates that something is not supported. And as we see here, it says Tornado VM has an unsupported data type. So the user can change it. It is an indicative message that they need to perform some action. I have also, and also, yeah, if we see here, we see that these tasks are not recognized as valid tasks. So Tornado VM has not listed them as ready for dynamic inspection. A second example that we have is the throws example. So as we see here, this add method is valid because I have commented out the throws exception. But if I go back, now it is red and has not been identified as a valid task. And here, if we click, we see that there is an incompatible thrown types exception in this message from Tornado Inside. Okay, and the final part that we have prepared for the demo is this add method. In a sense, it takes three arguments, A, B, and C. It creates a new primitive array inside. Actually, it declares it and will create a new object for every iteration that we run. This, if we consider that we have that parallel annotation, it would mean that every GPU thread would have to create a new memory space inside for the array D. And this is not supported, but if we see it as a code syntax, this is valid for Java. And that's why we see here that the task has been detected. But if we try to run dynamic inspection, we see that we get this kind of compiler error in the Tornado Inside console. And we see here that this behavior has not been implemented, and a message that says dynamically sized arrays, the declarations of these arrays is not supported. So yeah, this is the demo that we have prepared. Let's go back to the slides. Okay, so we have enhanced developer experience. I mean, speaking from the Tornado VM team, we have the configuration panel to define the Tornado VM path, JDK, and the indicative array sizes. We have a dedicated tool that at code time during development can identify valid tasks or invalid tasks. We support static and dynamic compilation, so static analysis and dynamic analysis in a sense, and we generate kernels, OpenCL kernels. Not only OpenCL, but in this MacBook, we support only OpenCL. We can also support SPLASH'25 kernels or CUDA kernels. And regarding impact and adoption, we can detect errors before runtime, so during coding. We can improve developers' productivity, and we have seen that from our team. And this has been used for 2 heavy use cases that we have. The one is ray tracing, the second is GPU Llama 3, which is the actual implementation that Michal shared in the previous talk, where we can actually have hundreds of tasks chained together, so we can actually see if there is any issue during the coding in the code syntax. So in summary, if we reflect back, we have this kind of question: can we educate Java programmers for GPU programming? And the reality is that we showed you that with tools like Tornado Viz and Tornado Insight, we can actually help Java programmers to understand how GPU programming works. So as future roadmap, we want to enhance this work with smarter dynamic diagnostics. We want also to extend it with auto-completion. And we have already extended Tornado Insight with more assets like Tornado Viz. And the idea is that because we're generating GPU code, I think it's a good idea to auto-verify it when we're returning it back to the users. And we welcome many contributions from the community, because it is open source. So in conclusion, we have already shown you that Tornado VM unlocks performance in previous talks. We show you here that Tornado Insight and Tornado Viz can unlock usability. So together, hopefully, they can make Java development for GPUs more seamless and automated. So I think, yes, I'm ready to accept any questions. Thank you very much.
Thanks, Thanos. Let's take a question or two. I think everyone's very tired at the end of a long day. Any questions? The audience is silent. Tell us about your plugin. Do you create IntelliJ plugins as Java code, or what? What's the complexity of the plugin implementation?
So the implementation is purely in Java, and we have utilized the APIs from JetBrains.
Yeah.
It has been very easy, I would say. I mean, they are documented. And the idea, I think the most interesting part coming from a compiler group is that JetBrains, they have some objects that enable you to see inside the method, you know, the fields. So we have used them in order to do all these kind of inspections in the inspection mode.
Yeah, that's nice. Very good. Oh, we do have a question. Well done. Come to the microphone, please.
I do have a question. Could you use this with the FPGA backend as well?
Yes. Yeah, definitely.
Okay, so it's not just for GPUs.
No, but as long as you have an FPGA on your system. So it means that on this laptop, I wouldn't be able.
But the constraints would be different.
The constraints regarding the syntax, no, because the Tornado VM API is hardware agnostic.
Okay, I see.
But the output from the JIT compiler, from the dynamic inspection module, it could be different because we have different phases in the compiler for the FPGA backend.
Okay, so even if you had a backend where you could resize, you have to constrain it because of the GPU?
I wouldn't say constrain it.
I mean, resize the array list.
Yes. It depends also on the size that you have on the GPU, on the memory size.
Okay, thank you.
And thank you for your question. Let's thank Thanos one last time.
Thank you very much.
Our chair, Tomohiro, is going to make some final remarks. Thank you.